R is one of the most widely used languages in the field of data science. If you should want to do anything related to statistics or related to data science, then R needs to be your go-to language. Understanding this, we have brought you this R programming full course. Now, let's quickly have a glance at the agenda.
Before we get started, I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.
So we'll start off by learning some of the fundamentals in R language, and then we'll look at the different data structures in R, which would be vector, list, data frame, and so on. And then we'll see how to do data manipulation with the dplyr library. And then we'll go ahead and do data visualization with the ggplot2 library. After that, we will perform exploratory data analysis. And then finally, we'll be implementing some AI related tasks with R.
So we'll start by installing R, and you can install R from this particular site over here. So we've got cran.rproject.org. So let me just click on this link over here. Let me just wait till this loads up. Right. So we've got different versions of R. So if you're using a Linux system, then you can download R for Linux. If you're using a Mac system, then you can download R for Mac. And if you're using a Windows system, then you can download R for Windows. And since I'm using a Windows system, I'll be downloading R for Windows. So I'll click on this link. All right. So again, we have this option to install R for the first time. I'll click on this. And this is the latest version of R 3.6.1 for Windows. I'll click on download and the download would start. Now, after installing R, we would also need an IDE. So IDE basically gives you certain features so that implementing code becomes much easier. So if you have work with Java, then you would know that there is an IDE for Java called as Eclipse. So analogous to that, we also have something known as RStudio when it comes to R. So RStudio is the IDE which makes coding with R extremely easy. And to download RStudio, you can go to this particular site over here, rstudio.com. So I'll click on this link. All right, so this is the site, and over here we'll be basically downloading the free version of it. So I'll click on download, and we've got different versions over here again. So if you're using a Ubuntu system, you can download it for Ubuntu. Then we've got Debian, Fedora, and so on. And since I'm using a Windows system, so I'll download the 64-bit version for the Windows system. All right. So now the download for R and RStudio is complete. Now let's run to the programming part. So we'll start by understanding what exactly are variables in R. So simply put, variables are just temporary storage spaces. So let's take this example to understand variables in a better way. So you see this shopping bag over here. Now consider that you can only store one item in the shopping bag at one particular time, right? So what you do is you have the shopping bag with you, you go ahead and buy a phone, and then you take this phone and place this inside the shopping bag. So over here, this is your variable, and you are storing this particular data item, which is a phone, inside the shopping bag. So after some time, you decide that you don't need a phone and you actually need a pen. So you take this phone out and you put this pen inside this shopping bag over here. And again, after a while, you decide that you don't actually need a pen and you need a makeup kit. So again, you take out this pen from the shopping bag and then you place this makeup kit inside the shopping bag. So over here, this shopping bag is basically acting as a variable. So first it stores a mobile phone, and then it stores a pen, and then it stores a makeup kit. So this is what exactly is a variable. It stores temporary values inside it. Now going ahead, we'll work with these variables in RStudio. So this is RStudio, guys, and we've got all of these panes over here. So this is the script window where you can write all of your script. This is the console window where you can execute your code. And then we've got the environment window over here, which basically shows you the different variables you have. And then we've got this packages and plot window. So this basically shows you the different packages which are already installed, and you can have a glance at all of the plots in this plots window. All right, so let's go ahead and see an example of variables. So I'll go ahead and create a variable with the name var1, and inside this I will store the value, let's say phone. Now I'll print this out, var1, right? So the value is phone. Now what I'll do is inside var1 again, I will store the value pen. Now let me print out var1 over here. So initially the value stored inside var1 was phone, and then I change this value to pen, and when I print it out, the value is pen. So this is how a variable works. So it basically stores temporary values and you can change that value whenever you want. So again, I will go ahead and change this value. So instead of pen, I will store, let's say, makeup inside this. Now I'll print this again, right? So now the value of var1 is makeup. So this is how variables work in R. Now every variable is basically associated with a data type, and every data can be of different types. So data can be of numeric. So if you got numbers such as 3.14, 75 and 500, this is basically numeric data type. And then we also have character data types over here. So if you have names such as Sam and Bob, or if you say sentences like I love pizza or my name is Sam, so this is basically character data type. And then we've got the logical data type, where you basically have two values. First value is true and then the second value is false. And then finally we've got the complex data type, and in complex data type you have two parts. First is the real part and then you have the imaginary part. So over here we've got numbers such as 7 plus 5i and minus 3 minus 9i. So in 7 plus 5i, 7 represents the real part and 5i represents the imaginary part. So these are the different data types which can be present in R. Now again, let's go back to RStudio and work with some data types. So I'll clear this out. Now again, I'll take a variable with the name var1. I'll put in equal to, and let me store a numeric value inside this. So I'll store, let's say, 12.34, and then let me print this out, var1. Now let me check the class of it. So class of var1. So inside the class function, I am passing on this variable1 object, and you see that the class of this variable is basically numeric. Now in this var1, what I'll do is I will basically store a character value. So inside this, now I'll store, let's say, Sam, and then I'll print out var1 over here. Now let me check the class of it. So class of var1, right? So initially when we had given a numerical type to this var1, the class was numeric. After some time, when we went ahead and stored the value Sam inside var1, the class changed to character. So the class of the variable basically depends on the type of the data which you store inside this variable. So if you given a numeric type data inside the variable, the class of the variable would be numeric. If you given a character type data inside the variable, the class of the variable would be character. Similarly, if you given a logical type data inside the variable, then the class of the variable would be logical. So that is what we're going to do now. So I'll type var1 over here, and inside this, let me give in a logical value. So I'll type in true over here. And when it comes to logical values, in R you have to keep in mind that all of the letters have to be capital. So TRUE, all of the letters have to be capital. Now let me check the class. So class of var1. Right, so we see that this is logical now. Now finally I'll store a complex value inside this. So var1 equals to, I'll say 13 plus 6i. Now let me check the class of it. So class of var1. So see that this is complex. So these are different data types which can be present in R. Now going ahead, we'll work with operators in R. So these are the different types of operators in R. We've got assignment operators, arithmetic operators, relational operators, and logical operators. So we'll be starting with assignment operators. So with the help of assignment operators, we can basically assign a value to a particular variable or a particular function, right? So this is what assignment operators are used for. So let's say I have a variable with the name A and I want to assign a value to this. Now there are three varieties of assignment operators. First is the equal to operator. So I'll just give in the equal to value and I'll store the value 8 inside this. So what I'm basically doing is I am storing the value 8 inside this variable A. Now let me print this out, right? So we see that we have assigned the value 8 to A. Now I have another variable with the name B and I will use the second type of assignment operator. So this time I'm using a less than symbol, and after that I'm giving a hyphen, and then I'll store another value inside this. So let's say I give in the value hello. Now let me print this out. Right. So now I have assigned the value hello to the variable B with this assignment operator. And then finally we have the third assignment operator where we actually given the value first. So I'll give in the value which is true. and then I given this assignment operator. So over here, I given the hyphen first, and then I given the greater than symbol, and then I'll given the name of the variable where I want to store. So I want to store this in, let's say, final. All right, now I'll print out final over here. So we have successfully stored the value true inside final. So I'll just print out all of these three assignment operators. First is the equal to operator, and then we've got this operator over here where we given less than symbol and then we given hyphen, and then we've got the third assignment operator where we given hyphen and then we given the greater than symbol over here. So after the assignment operators, we've got the arithmetic operators, and arithmetic operators are used to perform simple mathematical functions such as addition, subtraction, multiplication, and division. So we'll see an example of each of these. Now for doing that, I'll basically create two variables over here. In the first variable, which is num1, I'll store the value 10, and then I'll go ahead and create the second variable with the name num2, and inside this I will store 20. So now I've got my variables over here. Going ahead, I'll perform some mathematical operations upon these two variables. So let me just print out these two variables in the console first. Right. So I have successfully created num1 and num2. Now I'll type in num1 plus num2. I'll copy this and I'll paste it over here. And we get the result 30, because when you add 10 and 20, you get the result 30. Now similarly, I'll perform the next operation over here, which would be num1 minus num2. Because when you perform 10 minus 20, you get a value of minus 10. Now I'll perform the multiplication operation. So it would be num1 into num2. And when you perform 10 into 20, you get a value of 200. And then finally, we'll perform the division operation, which would be num1 divided by num2. And you get a value of 0.5 because 10 divided by 20 is 1 by 2. So these are some of the basic arithmetic operations which you can perform. So next up, we have the relational operators. In relational operators, we've got these symbols over here. So you've got greater than symbol, you've got less than symbol, you've got double equal to, and you've got not equal to over here. Now again for this, let me just use the same numbers of num1 and num2. So I'll type in num1 equals 10, and then I'll type in num2 equals 20. I'll copy these two variables and I'll paste them over here. Now let me start off with the greater than symbol. So I'll type in num1 and then I'll put in the greater than symbol, and then I'll give in the second variable, which is num2. So I'm basically checking over here if num1 is greater than num2. So we get a false value. Now we get a false value because num1 is actually less than num2, or in other words, 10 is actually less than 20. Going ahead, we'll use the second relational operator, which is less than. So now we are checking if num1 is less than num2. And we get a true value because 10 is actually less than 20. Going ahead, we have the double equal to operator. So over here, I'll put in double equal to. So with the help of double equal to operator, we are checking if the values stored in both of the variables are equal or not. Again, I'll hit enter. So we get a false value because 10 is obviously not equal to 20. And then finally, we have the not equal to operator. So the not equal to operator is given like this. You given the exclamation symbol and then you given the equal to operator. And then we get a true value because 10 is obviously not equal to 20. So these are some of the relational operators. Going ahead, we'll work with logical operators. And to work with logical operators, we'll create two more variables. So I'll create a variable with the name log1 and I'll store, let's say, true in this. And then I'll create another variable with the name log2 and I'll store false in this. Alright, so I've got my two variables ready. Let me execute them first. So I've got log1 and log2 ready. And the two logical operators which we have are basically and or operators. So let's understand a bit about the and operator and the or operator. So the and operator basically gives a true value if both of the operands are actually true. So let's understand this over here. So over here, I'll type in log1 and log1. So we know that the value stored in log1 is true. So when you say true and true, you get a true value. Now let me type in log1 and log2. We get a false value because true and false become false. Similarly, let me type in log2 and log1. Again, we get a false value because both of them have to be true. But over here, log2 is false. Now let me type in log2 and log2. Again, we get a false value because both of the operands have a false value in them. So when it comes to the AND operator, we have a true value only when both of the operands are equal to true. So OR operator gives a true value when any of the operands has a true value, and it gives a false only when both of the operands have a false value. So again, let's understand this with an example. So log1, I'll give in the OR operator, and then I'll type in log1. So true or true. So we get a true value, obviously. And then I'll type in log1 or log2, which basically comes to true or false, which is true again. Now I'll type in log2 or log1, again get a true value. And finally, let me type log2 or log2. Now since log2 is false, so we are basically trying to check if false or false. And since both of the operands are false, we get a false value over here. So these are the logical operators.
So just a quick info. If you're looking forward to pursue a post-graduation course in the field of data analytics, then Great Learning offers the Business Analytics and Business Intelligence program in collaboration with Mecom School of Business at University of Texas Austin and Great Lakes, India. The faculty pool comprises of leading academicians and industry practitioners in the field of data analytics. And you can check out the course details in the description mentioned below. Now we come to the main part of R, where we'll be learning about the different types of data structures in R. So we've got vector, list, matrix, array, factor, and data frame. And we'll be starting off with the simplest data structure in R, which is basically a vector. So a vector is a linear homogeneous data structure. Now, what do I mean by a linear homogeneous data structure? It is called a linear data structure because it has just one dimension. And it is called a homogeneous data structure because you can store elements of only one particular type in this data structure. So let's go to RStudio and perform some examples with vector. So let's go ahead and create our first vector over here. So I'll give the name of the vector as vec1. And to create a vector, you would have to use this C operator, which basically stands for the combine operator. And inside this, I'll give in some values. So I'll give in all the numerical values over here, 1, 2, 3. I'll copy this and I'll paste it over here. Now let me print vec1. So see that this is a linear data structure which has only numerical values present in it. Now let me check the class of it. Class of vec1. Right, so this is numeric. Now let me create a character vector. So I'll type in vec2 over here, and inside this I'll type in A, B, and C. Now let me copy it and paste it over here. Right, so let me also print vec2. So we see that this is a character vector which comprises of the elements A, B, and C. So class of vec2. So we see that this is of character type. Alright, now I'll go ahead and create a logical vector with the name vec3. And inside this, I'll be storing some true or false values. So I'll type in true, false, and true. I'll select this and I'll paste it over here. Right, so this is a logical vector which has these three values, true, false, and true. Let me also check the class of it. So class of vec3 is logical. Now let me do something interesting. What I'll do is I will create a vector which should have both numerical values and logical values present in it. Now let me actually do something interesting. So now I'll actually create a vector which would comprise of both numerical values and logical values. And I'll name this vector as mixbag1. So let me give in the values inside this. So the first element would be 1, second element would be true, and then I'll give in 2, and then I'll give in false over here. So now let me go ahead and print this vector over here. So this has actually been executed. But at the beginning, I've told you guys that a vector can only comprise of homogeneous values. But this vector with the name mixbag1 has heterogeneous values, which are basically numbers and logical values. So how has this vector even been executed? So to understand that, let me actually print out the elements which are present in this vector. So over here, you see that these logical values have been coerced into numeric. So this element 1 is 1 over here. True has been coerced into the number 1. 2 is 2,
and this value false has been converted into the number 0. So when you put in numbers and logical values into the same vector, the logical values are basically coerced or converted into numbers, and that is why we only have homogeneous elements in this vector over here. So even though we are passing in heterogeneous elements, they are being converted into homogeneous, and over here there is greater precedence for numeric values than logical values. So that is why all of the logical values have been converted to numeric. Now let me create a similar vector where I'll be storing the numeric values along with the character values over here. So I'll type 1, A, 2, B, and then I'll also type in 3 over here. And I'll actually name this to be mixbag2. Let me change the name to be equal to mixbag2 over here, and let me print it out. Alright. Now what do you think would be the answer? So let me just print it out and show you the result. So over here we see that these numeric values have been coerced into character. So this number 1 has been converted into a character 1. This number 2 has been converted into a character 2, and this number 3 has been converted into a character 3. Now to confirm it, let me also check the class of it. So I'll type in class of mixbag2, and we see that this is of type character. So when it comes to numeric values and character values, then character values take higher precedence over numeric values. And then let me create one final vector where I'm basically storing all the numeric values, character values, and the logical values in the same vector. And I will name this as mixbag3, and inside this I'll type 1, and then I'll type in A, and then I'll give in the value true over here. Then I'll type in 2, and then I'll type in B, and then let me give in the value false. So this vector has numeric elements, logical elements, and character elements. Mixbag3. Now let me print this out. So this time we see that all of the elements have been converted into character. So this means that character has the highest precedence, then it is numeric values, and then it is the logical values. So first is character, then comes numeric values, then come the logical values. Again, let me check the class. So class of mixbag3, and we see that this is of type character. Right. So we have this mixbag3 with us. Now what I'll do is I'll actually try to extract some individual elements from this entire vector. So let's say if I only want the second element from this entire vector. So let me try to extract the second element. So the name of the vector is mixbag3. To extract the element, we have this indexing operation. So we'll give in parenthesis, we'll give in this square braces over here, and then I'll give in the index number. And when it comes to R, the indexing starts with 1. So this is element which is present at index 1, and then this is element which is present at index 2. True is the element which is present at index number 3. So if I want the element which is present at index number 2, inside this I'll type in 2. So I have successfully extracted A from this entire vector. Similarly, if I want to extract this last element over here, so this is 1, 2, 3, 4, 5, 6. So element which is present at index number 6. So first I'll give in the name of the vector which is mixbag3, and inside the parenthesis I will give in the index number which is 6. So we see that we have extracted false. Now if you wanted to extract a series of values over here, so let's say I wanted all values starting from true and then going on till B. So this is starting from index number 3 going on till index number 5. So first I'll have to give in the name of the vector. Inside parenthesis I'll give in the starting index number which is 3. After that I'll give in colon, and after that I'll give in the ending index number which is 5. Right, so I've extracted true, 2 and B. And then if you wanted to extract some random index values from this vector, so let's say I wanted to extract only the first element and the last element from this entire vector. So for that you'll give in the name of the vector, you'll give in parenthesis over here, and inside this you will use in the combine operator, and inside the combine operator you will give in the index values. So I want the element which is present at first index and then the last index which is basically 6. So I have successfully extracted the element which is present at first index and also the element which is present at the last index. And this is how we can create vectors and extract individual elements from vectors. So this was the first and the simplest data structure, which was basically a vector. Now we'll head on to the second data structure, which is list. So a list is a linear homogeneous data structure. Now, a linear homogeneous data structure basically means that it is present in only one dimension, and the data types which go into this data structure could be of multiple types. So a list can store, let's say, a numeric value, a character value, and a logical value, and these individual elements will retain their identity. So let's create our first list, and I'll given the name of the list to be L1. And to create a list, we'll be using the list function. Now inside this, I'll give in the element. So the first element is the number 1, and then I'll give in the second element, which is the character A, and then I'll give in the third element, which is basically the logical value true. I'll copy this and I'll paste it over here. Alright, so we have created this list. Now let me check the class of this. So class, inside this, I'll pass in the object L1. So we see that this is of type list. Now let me check the class of the individual elements of this list. So I'll actually print out L1 over here. So we see that we've got 3 different components over here, and these 3 different components have their identities maintained. So 1 is a numeric value and it is retained as a numeric value. A is a character value and it is retained as a character value, and true is a logical value and it is retained as a logical value. So just to be sure, I'll use the class function and I'll check the class of all of these individual elements. So I'll type in class. Inside this, I'll type in L1. Now to get the individual entities, you would have to give in double braces over here. So you'll type in double braces, and then to get the first component, you'll type in 1. So you see that 1 is of type numeric. And then I'll go to the second component, which is basically present at index number 2. So we see that A is of type character. After that, I'll give in the third index value. So see that this is of type logical because the value is true. So we see that in a list, the identities or the individual identities of all the elements is retained. Now let me go ahead and create another list where I basically have 3 vectors inside this list. So I'll type in list. The first component would be basically a vector which would comprise of all the numerical values. The second component would be another vector which would comprise of all the character values. So it'll be A, B, and C. And then we've got the third vector over here, which would comprise of all the logical values. So it'll be true, false, and true. Let me print this out. So this is L2 over here, which comprises of 3 components. The first component is a numerical vector, the second component is a character vector, and the third component is a logical vector. Now let's go ahead and extract some individual entities or elements from this entire list. Now let's say I'd want to extract this element C from this entire list L2. So this is the third element of the second component. So this is how we can extract. I'll type in the name of the list, which is L2, and then I'll give in double braces. Now inside the double braces, I'd have to give in the component number, which is 2. After that, I'll give in braces again, and then I'd have to give in the element index in the second component. So the element index is 3. So we have extracted C from this entire list. Similarly, if I had to extract this false value from the entire list, so this is the element at index 2 of the third component. So let me just print out L2 again. Now I'll type in L2, I'll give in 2 braces over here, and this is the third component. I'll type in 3, and inside the third component, this is the second element. Right, so I have extracted false from this entire list. So vector and list were the 2 basic linear data structures. And now we'll head on to the multidimensional data structures. So we'll start off with matrix, which is basically a 2-dimensional data structure. So it is actually a 2-dimensional homogeneous data structure which comprises of rows and columns. Now let me create the first matrix. I'll type in M1 over here. And to create a matrix, we have this matrix function. And I'll just pass in some values over here. So I'll use the combine operator and I'll pass in all of the elements from, let's say, 1 to 6. I'll take this, I'll copy it and I'll paste it over here. Right, so we have created a matrix where all of the elements are basically present in different rows. So we have a 1 column 6 row matrix, or it is a 6 cross 1 matrix. Now this is not ideally what we want. we actually want a matrix which would have some number of rows and some number of columns. So to do that, we have the n row attribute inside this matrix function. So this is the same function over here, matrix. The first parameter is basically the vector which would give in all of the elements. Now after this, I have the n row parameter where I set the number of rows to be equal to 2. And then I have the n col parameter where I set the number of columns to be equal to 3. So I am creating a 2 cross 3 matrix over here. M1. So we have a 2 cross 3 matrix where we have 1, 3, 5 in the first row and 2, 4, 6 in the second row. Now if you look at this matrix, you see that these elements are arranged column wise. So you have 1, 2, and then you have 3, 4, and then you have 5, 6. But what if I wanted to arrange these elements row wise? So for that purpose, we have the by row attribute. So I'll type in by row and I'll set the value to be equal to true. Now let me print out M1. So this time we have these elements arranged in the row wise order. So by default, these elements are arranged in column wise order. And if you want to arrange them in row wise order, then we have to set the by row attribute to be equal to true. Now let me go ahead and extract some individual elements from this matrix. So now I want to extract this element 5 or this value 5 from this matrix. So I'll type in M1, I'll give in parenthesis over here. And this value 5 is present at row number 2 and column number 2. So I'll type in 2, 2 and I have extracted 5. Similarly, if I wanted this 3 over here, this is present at row number 1 and column number 3. So I'll type in M1, I'll give in the row number which is 1 and then I'll give in the column number which is 3. Right, so we have extracted the element 3 from this entire matrix. Now we'll head on to the next type of data structure, which is basically array. So you can consider array to be just an extension to matrix. So matrix is a two-dimensional homogeneous data structure, while an array is a multi-dimensional homogeneous data structure. Now before we create the array, we'll actually create two numerical vectors. I'll create vec1, which would have, let's say, all the elements starting from 1 to 6. So 1, 2, 3, 4, 5, and 6. And then I'll create the next vector, which is vec2, which would have all the elements starting from 7 to 12. So 7, 8, 9, 10, 11, and 12. Now let me print out these two. So I've got these two numerical vectors ready. Now I'll go ahead and create my array. So I'll type in A1, and to create an array, we would have this array function. And inside this array, the first parameter which would be giving in would be the data. And the data is basically coming in from these two vectors. So I'll combine these two vectors over here. And to combine these two vectors, I'll use the C operator. And inside this, I'll pass in vec1 and vec2. So I've given the data. Now after this, I would have to set the number of dimensions over here. So I'll type in dim to set the number of dimensions. You can consider array to be basically matrices which are stacked on top of each other. Now what I want to do is I basically want to create two matrices of the size 2 cross 3 which are stacked on top of each other. So let me repeat this again. I want to create an array which would comprise of two matrices of the size 2 cross 3. So over here, the dimensions would actually be 2, 3, 2. So this means that I am creating an array which is of two dimensions, and in those two dimensions, the size of the matrix is 2 cross 3. So let me copy it and let me paste it over here. Let me print A1, and this is what we have. So we have created an array which comprises of two matrices, and the size of both of these matrices is 2 cross 3. And we have 12 elements in total, right? So 2 cross 3 into 2 gives you 12 elements. Now let's see how can we extract individual elements from this entire array. So I want to extract this element 11 from this array. So this is present in the second matrix, and the row number is 1 and the column number is 3. So I'll give in the name of the array first, which is A1. I'll put in these two commas, and then first I'll give in the matrix number of the dimension number. So it is 2. And then I'll set in the row number, which is 1. And then I'll set in the column number, which is 3. So I have extracted this element value 11 from this entire array. Now we'll head on to the next type of data structure, which is basically a factor. So you can consider a factor to be a data structure which holds categorical values. Now, factor variables or categorical variables become very important during the model building process. So let's actually understand about it. So to create a factor, all you have to do is type in factor over here, and inside this I'll create a character vector. So let's say I create a character vector with these three colors. I'll type in blue, and then I've got yellow over here, and then the next color which I have is red, and I'll store this in a new object and name that object to be color. So let me print this out. So we have basically created a factor object which comprises of these three categories, which are blue, yellow and red. Now let me actually repeat these colors and let's see what would be the result. So we've got blue, yellow, red. So I'll add yellow 2 more times over here. Let me print out color again. Right. So this time these are all the elements: blue, yellow, red, yellow, yellow. But if you look at the levels, you see that the levels remain the same. We've got blue, we've got red, and we've got yellow. So this is how you can work with categorical variables or factors in R. And then we've finally got a data frame. So a data frame is a two-dimensional heterogeneous data structure in the form of rows and columns. And this is the most important data structure when it comes to R, because you'll be implementing most of the data manipulation and data visualization operations on this data structure called as data frame. So let's go ahead and actually create a data frame. So to create a data frame, you would be using this data.frame function. And I want to create a data frame which would comprise of two columns. The first column is basically the name of the fruit, and the second column is basically the cost of the fruit. So let me create the first column, which would be fruit name, and the values to this column would be basically coming from this particular vector over here. So the names of the fruits are apple, banana, and then we've also got an orange. So this is the fruit name, and then let me go ahead and give in the fruit cost as well. So this would be my second column over here, fruit cost. So let's say apple costs around $100, and then we've got banana which costs $50, and then we've got an orange which is in between and that costs $75. So over here we are basically creating a data frame which has two columns. So the first column is fruit name and the second column is fruit cost. Now let me store this in a new object and name that object to be fruit. I'll copy it and I'll paste it over here. Let me run this. All right. So you can actually have a glance at the data frame with the help of this view function. So I'll type in view, and inside this I'll pass in the object which is fruit. So we have created this data frame which has these two columns, fruit name and fruit cost. So we've got this data frame with us. Now let's see how can we extract individual columns. So first we'll give in the name of the data frame which is fruit, and then I'll give in the dollar symbol, and then I'll give in the name of the column. So let's say if I want to extract only the fruit name column, I'll select fruit name. So first the name of the data frame, and then the dollar symbol, and then the name of the column. So this is how we can extract the first column from this data frame. Similarly, if I want to extract the fruit cost column, so over here I'll select fruit cost, and then we have extracted the second column from this entire data frame. So extracting a column from a data frame is extremely simple. All you have to do is give in the name of the data frame, then the dollar symbol, and then the name of the column. So these were all of the data structures which were present in R. So we've looked at vector, list, matrix, data frame, and array. Now let's go ahead and work with some inbuilt functions. So we'll look at all of these different inbuilt functions over here. And we'll be working with all of those inbuilt functions on top of the iris dataset. And as I've already told you, to have a glance at the dataset, we'll be using the view function. So I'll type view of iris. So this iris dataset basically comprises of 5 columns in total, which are sepal length, sepal width, petal width, and species. Now this dataset basically comprises of the 3 species of the iris flower, which are setosa, versicolor, and virginica. And we've got the corresponding sepal length, sepal width, petal length, and petal width corresponding to those 3 species. Alright, now let's work with those inbuilt functions. So the first inbuilt function was the structure function. So all you have to do is type in str, and inside this I will pass in the data frame which is iris, and this gives you the entire structure of the data frame. So over here this tells you that there are 150 observations of 5 variables. Or in other words, there are 150 rows in this data frame and 5 columns in this data frame. And then you also have a bit of description about each column. So you see that sepal length is a numerical column, and these are some of the first few values in this column. And then we've got sepal width, which is also a numerical column. Then we have petal length and petal width, which are also numerical columns. And then finally, we have the species column, which is basically a factor variable with 3 levels. So this is why the structure function is used. So after structure, we've got the head function. So with the help of the head function, we can have a glance at the first 6 records of this data frame. So inside this, I will pass in the name of the data frame, which is iris. So we've got the first 6 records of this data frame over here. Similarly, if you want to have a glance at the first 10 records, then all you have to do is use in n over here and then given the value 10. And then you can have a glance at the first 10 records of this entire data frame. So similar to the head function, we've also got the tail function with which you can have a glance at the last 6 records of this data frame. So first, all you have to do is pass in the name of the data frame inside this. And these are the last 6 records which are present in this iris data frame. So starting from row number 145 going on till row number 150. And these are the last 6 records present in this data frame. Similarly, if I want to have a glance at the last 10 records of this data frame, I'll use n equals and then I'll pass in 10 inside this. And these are the last 10 records which are present in this data frame. And then we have the table function. So table function is used to identify the frequency of the categorical columns or to understand the count of different levels which are present in a categorical column. So I'll type in table. And the only categorical column which is present in this iris data frame is the species column. So I'll select the species column, iris $species, and we see that there are 50 entries of setosa, 50 entries of versicolor, and 50 entries of virginica. So this is how table function can be used to get the frequency of each of the different levels of a categorical column. Next, we've got some arithmetic functions. So we've got min, max, mean, and range. So if you want to find out the minimum value in a particular column or a particular vector, then we can use the min function. So inside the min function, what I'm doing is I'll pass in this sepal length column. So I want to find out the minimum value of sepal length. Iris $sepal length. So we see that the minimum value of sepal length is 4.3. And then I'd want to find out the maximum value of sepal width. So to find out the maximum value, I'll use the max function. And inside this, I'll pass in iris $sepal width. And the maximum value of sepal width comes out to be 4.4. And now I'd want to have a glance at the mean of petal length column or the average petal length of the different records which are present in this data frame. So I'll type in mean iris $petal length. And the mean petal length value comes out to be 3.758. And then we've got the range function, which basically gives you the minimum value and the maximum value, which is basically the range. So I'd want to find out the range of this petal width column. So I'll type in range, and inside this, I'll type iris $petal width. And we see that the minimum value of petal width is 0.1 and the maximum value of petal width is 2.5. So these were some of the inbuilt functions in R. So next we have decision-making statements. So with the help of decision-making statements, we basically given a condition, and on the basis of that condition, we make a decision. So we've got if and if else. So let's start with the if statement. And again, we'll be working with the same iris dataset to implement the if statement. So let me open a new script window over here. Now I actually want to make a condition where I am checking if the first cell value in the sepal length column is greater than 4. So I'll type in if and I'll put in braces over here. So this is basically curved braces over here. And inside this, I'll give in the condition, which is iris $sepal length. And since this is the first cell in the sepal length column, I'll use in parenthesis and I'll type in 1. Now after this, the condition is I want this value to be greater than 4. So if the value is greater than 4, then I'd want to do something. So I'll just print out the sepal length is greater than 4, I'll copy this and I'll paste it over here. And we see this result, the sepal length is greater than 4. So this is how the if condition works. So we give in a condition, and if that condition is evaluated to true, then we go ahead and perform an action. And if that condition is evaluated to false, then nothing happens. So over here, what I'll do is I'll actually change this condition. So this time I want to check if the value which is present in the first cell is less than 4. And if it is less than 4, do something. So I'll copy this, I'll paste it over here, and we see that we don't get any result. And this condition actually fails because sepal length is greater than 4 and not less than 4. And that is why we don't get any result over here, right? So when we gave in the first condition where we checked if sepal length is greater than 4, it was evaluated to true and then we got the result. But then again, when we used less than symbol instead of the greater than symbol, this condition evaluated to false because obviously the sepal length is greater than 4. So that is why nothing happened. So this is where the if-else statement comes in. So first we use the if statement, and then if it evaluates to true, we do something else. Now this else checks that if the if condition fails, then do something else. Now this might seem complicated, so let me just give an example to you guys over here. So I'll type in if, and then I'll give in the first condition iris $sepal length, and then the first cell, if it is less than 4, then you would have to print out sepal length is less than 4. After this, you'll give in the else condition, and then you'll type print sepal length is greater than 4. Now let me print it out over here. So we get this result, sepal length is greater than 4. So this is how this statement basically works. It starts with the if condition and checks if the sepal length, this particular record, the value present in this record is less than 4. And if it is true, do this. And since this has been evaluated to false, it does not execute this and comes to the else statement, and then it prints out sepal length is greater than 4. Now the looping statements are basically used to repeat a particular task, and today we are going to look at the for loop and the while loop. So we'll start with the for loop. So the for loop is used to iterate over a particular list or a sequence of items. So let's see an example in RStudio. Now I'll go ahead and create a vector again. So I'll name this vector as vec1, and I'll store all the elements from 1 to 9. Let me print out vec1 over here. So this is our vector, which would comprise of all of these elements starting from 1 to 9. Now, using the for loop, what I'll do is I'll add 5 to each of these individual elements. So let me show you guys the syntax. I'll type in for, and then I'll type I in vec1 print I plus 5. I'll copy this, I'll paste it in the console. So initially the value of I is taken to be 1. Now let's understand this for loop properly. So this for loop iterates till the end of the last element. Now let's understand this for loop properly. So for I in vec1, so initially the value of I starts at 1 and then it goes on till it reaches the last element. So it is 1, it comes inside the loop and 1 is added to 5, then the value becomes 6 and that is printed. And then again the for loop starts, the I value is incremented and I becomes 2. So 2 plus 5, it becomes 7 and that is printed. And then I's value is again incremented, it becomes 3, 3 plus 5 and then we have 8. So this goes on till the last element in the vector is reached. So the last element in the vector is 9. So 9 plus 5 becomes 14 and then we print it out. Now after that, if you try to increment the value of I, it will not be incremented because it has already reached the last element. So it will end when it is 14. So this is how the for loop works. Now let's work with the while loop. So it is sort of similar to the for loop and it is also used to iterate something. But the only difference is it iterates a particular task till a condition is met. So now for this for loop, I'll actually use a counter. So I'll set I value to be equal to 1, and then I'll type while over here, and I'll type while I is less than 9. So this is the condition, and this loop will iterate till the condition is satisfied while I is less than 9, and I'll print out I, and then I'll print out I plus 5. After that, I'll increment the value of I with 1. So I becomes I plus 1. Let me copy all of this and let me paste it in the console. Right, so this goes on till 13 over here. So what is happening is initially I's value is 1. So the condition is checked over here. Is 1 less than 9? This is evaluated to true. So it comes inside the loop and 1 is added to 5, which becomes 6. So 6 is printed and then I's value is incremented by 1. So it is 2. Again, it is checked inside the while loop. So is 2 less than 9? So if 2 is obviously less than 9, so it comes inside the loop. 2 plus 5 becomes 7. So I's value is incremented till it is 8. So 8 is less than 9. It is true. It comes over here. 8 plus 5 becomes 13 and then it is printed. But after that, when I's value is incremented, this condition fails because 9 is not less than 9. 9 becomes equal to 9. And since the condition fails, this loop ends over here. So this is how we can work with the for loop and a while loop to repeat a certain task. Now let's head on to the user-defined functions. So simply put, user-defined functions can be invoked to perform a specific task. So that task could be anything. So let's say you want to create a calculator. Now to create a calculator, you want to create individual modules. So you want one module which is used for addition purpose, one module which is used for subtraction purpose, one module for multiplication purpose, and so on. So over here, you can use functions. So you can create a function with the name add 5, which would basically take in a number and add 5 to it. So if you pass in 5, it'll be added with 5 and then the value becomes 10. And then if you pass in the number 10, this function will take in 10, add 5 to it, and then the result which you'll get will be 15. So this is how functions basically work. So functions basically are used to perform a specified task, and whenever you invoke the function, that task can be implemented again and again. And this is the syntax to create a function. So you will use the keyword function, and inside this you will pass in a parameter which is x. And inside the body you will type in what this function is supposed to do. So I'll type in print x plus 5, and I'll store this in an object with the name add 5. So I am basically creating a function which takes in a parameter and adds 5 to it and prints the value. I'll copy this and I'll paste it over here. Now let me type add 5, and inside this let me pass in 1. So the result is 6. Similarly, I'll type in add 5 again, and I'll pass in the value 10. So we get a result of 15, and then I'll pass in, let's say 100, and I get a result of 105. And this is how you can create a user-defined function. So these were some of the basic operations with the R language. Now we'll head on and see what exactly is data manipulation and how can we perform data manipulation operations with R. So let's take an example to understand data manipulation in a better way. So let's say you're given a huge data set by your manager, which comprises of around 1 million rows and 10,000 columns. Now your manager gives you a task of finding out all of the employees from this data set whose salary is, let's say, greater than $100,000 and age is greater than 50. So how would you do it? Would you actually manually go through each of these 1 million rows and check the age of the employee and salary of the employee? Well, obviously you wouldn't, right? So this would be a huge task and this would also consume a lot of time. So this is where data manipulation operations comes in. So all you have to do is write in one simple line of code and you can easily extract all of those employees whose salary is greater than $100,000 and whose age is greater than 50. And to perform data manipulation operations with R, we have the dplyr package. So this dplyr package is based on something known as grammar of data manipulation, and it makes the data manipulation task extremely easy. So let's again head back to RStudio and work with the dplyr package. So we'll be working with this laptop's dataset to perform all of the data manipulation operations, and we've got all of these columns over here. Now let's see the number of rows and number of columns present in this dataset. So I'll type in n row over here and pass in the name of the dataset, which would be laptops. So see that there are 1303 rows or 1303 different types of laptops present. Now let me also check the number of columns present. So to check the number of columns, I've got the ncol function. And inside this, again, I'll pass in the laptops data frame. And there are 12 different columns present in this data frame. So there's a data frame which comprises of 1303 rows and 12 columns. Now let's look at the different columns of this dataset. So we've got the company or the brand name of the laptop. And then we've got the product name of the laptop. So if it's Apple, then what is the product name? It's MacBook Pro. Then we've got the type name. It's an Ultrabook. We've got the inches of the laptop. So what is the size of the laptop? So this Apple MacBook Pro, which is an Ultrabook, the size is 13.3 inches. Then we've got the screen resolution over here. Then we've got the CPU type. So over here, this laptop has basically Intel Core i5 with 2.3 gigahertz. And then the RAM of this laptop is 8 GB. Then we've got the memory of laptop over here. Then we've got this column which tells the GPU of this laptop. Then we've got the operating system of the laptop. So since this is a Mac laptop, the operating system is obviously Mac OS. And then we've got the weight of the laptop, and then we've got the price of the laptop in euros. So this Apple MacBook Pro costs 1339 euros. Right now my first task would be to load up the dplyr package. So I'll type in library and then I'll give in the name of the package, which would be dplyr. So this is how you load a package in R. So library of dplyr, and we have successfully loaded this package. Now before we load this package, you'd actually have to install this package. So to install the package, we've got this packages tab and we've got this install button over here. And inside this, you just type in the name of the package, which is dplyr. And if you click on install, the package would be installed. So I'll not click on install because I already have it installed over here, and I've also loaded up the package. Now I have already loaded the dplyr package and I have already loaded the laptops file. So to actually load a file in R, we'll be using this read.csv function. So let me just show you guys how this read.csv function works. So with the help of read.csv function, you can load a CSV file, and inside this, you'll just give in the path of the file over here. So this laptops.csv file is present over here. So inside this read.csv function, you'll just give in the path of the file. So this laptops.csv file is present in this path, D drive, slides and other files, Bharani, laptops.csv, and I'm storing it in a new object, and I'm naming this object to be laptops. And to have a glance at the dataset, all you do is use the view function and then give in the name of the data frame, which is laptops again, right? So this is a data frame. So we have successfully loaded this data frame. Now we'll go ahead and perform some data manipulation operations on this laptops data frame. So there's this select function from the dplyr package, which would help us to extract individual columns from the entire data frame. Now in this data frame, we see that there are not many columns, but consider a scenario where you have around 10,000 columns and you want to extract only 5 or 6 columns from all of those 10,000 columns. Now manually selecting those individual columns would be a Herculean task. So this is where select function comes into the picture. So let's work with the select function. So now what I want to do is I want to extract only the first column and the second column from this laptop's data frame. So this would be the way to do it. So I'll just type in the name of the data frame first, which would be laptops. And then we have something known as the pipe operator. So in the pipe operator, you give in the % symbol and then the greater than symbol and then the % symbol again. So this pipe operator basically helps you to connect an object with a function or one object with another object. So over here, what I'm doing is I am selecting the first column and the second column from this laptop's data frame. So I'll type in laptops over here and then I'll give in the pipe operator. Then I'll use the select function, which is part of the dplyr package. So if you have to use this select function, you would have to first load the dplyr package. And then inside this, you will give in the column numbers. And as we already know, the indexing in R starts with 1. So I want the first column and the second column, and I'm selecting these two columns from the laptop's data frame, and I am storing it in a new object, and I am naming that object to be, let's say, laptops 1, 2. Now let me open up laptops 1, 2. So this is my new data frame, which I've extracted from my original data frame over here, which has all of these columns. So from all of these columns, using the select function, I have selected only the first two columns. Now similarly, let's say if I wanted all of the columns starting from the column number 3 going on till column number 6. So this is how I'll do it. I'll start off by giving the name of the data frame first, which is laptops, and then I'll give in the pipe operator, and then I'll give in the select function. So since I want a sequence of columns, first I'll give in the starting index of the column, which would be 3. So 1, 2, 3, which would be type name, and then I'll go on till column number 6. So 3, 4, 5, and 6. So I'm extracting all of the columns from type name, inches, screen resolution, and CPU, and I'm storing it in laptops 36, view of laptops 36. Right, so I have extracted all of these columns from the original data frame. Now similarly, I can extract the columns from this data frame on the basis of the names of the columns instead of giving them the index numbers. So if I want the columns company, product, and price euros, all I have to do is give in the column names inside the select function. So again, I'll start off by giving the name of the data frame, then I'll use the pipe operator to join this select function and the data frame. And inside the select function, I'll give in the names of the columns which I want to extract. Column, so I want to extract company, product, and the last column, which is basically price euros, and I'll store it in laptop CPP. So view of laptop CPP, right? So I've extracted company, product, and price euros from this entire data frame. Now there are two interesting attributes inside this select function. So let's say I want to select all of those columns with start with a particular letter or end with a particular letter. Then for this purpose, we've got the starts with attribute and the ends with attribute. So from this data set, I'd want to extract all of those columns where the column name starts with the letter capital P. So I'll select this code over here and I'll paste it. So from the laptops data frame, I am selecting all of those columns where the column name starts with capital P. So inside the select function, I'll use this attribute starts with, and inside starts with, I'll give in capital P, and I'll store it in laptops underscore P, view of. Right, so I have extracted these two columns where the name of the column starts with capital P. I've got product and I've got the price in euros. And similarly, I'd want to extract all of those columns where the name of the column ends with small s. So this time I'll be using the ends with attribute. So from the entire laptops data frame, I am selecting all of those columns where the column name ends with small s, and I'm storing it in laptop small s, view of laptop small s. Right, so I've got these three columns over here: inches, obs, and price in euros. So this is how the select function works, which is basically used to extract individual columns from the entire data frame. So after the select function, we've got the filter function. And with the help of the filter function, we can extract records from the entire data frame on the basis of a condition. So over here we have the first condition. I want to extract all of those records from this laptop's data frame where the company is Dell. Or in other words, I want to extract only the Dell laptops from all of the laptops present in this data frame. So again, I'll give in the name of the data frame, which is laptops, and then I'll give in the pipe operator. And after the pipe operator, I'll give in the filter function. So again, filter function is a part of the dplyr package. So if you want to use the filter function, you'd have to load the dplyr package first. And inside this, I'll give in the condition where company is double equal to Dell. So wherever the company is equal to Dell. So let me go over here, right? So wherever inside this column you see, if the value is equal to Dell, then we'll extract all of those records and we'll store it in a new object, and we'll name that object to be laptops Dell, view of laptops Dell. So if you have a glance at this column over here, we've got 297 entries in total, or in other words, we've got 297 Dell laptops from this entire 1303 laptops. Now similarly, let's go ahead and give another condition. So this time from all of the laptops, I'd want to select only those laptops where the size of the laptop is greater than 15 inches. So this is the command for it. I'll give in the name of the laptop, then I'll give in the pipe operator, and then I'll join this data frame with this filter function with the help of the pipe operator. And inside the filter function, I'll give in the condition, which is basically the inches needs to be greater than 15. So inches is basically this particular column over here. right? So inches needs to be greater than 15 and I'm storing it in laptops 15 inch. View of laptops 15 inch, right? So if you have a glance at this, we see that the inch is greater than 15 in all of these records over here. So there are 835 entries in total, or in other words, out of the 1303 records, there are 835 laptops where the screen size is greater than 15. And with the help of the filter function, we can also give in multiple conditions at the same time using the AND operator. So this time I want to extract all of those laptops where the company name is Dell and the inches is greater than 15. That is, I want all of the Dell laptops where the screen size is greater than 15. So laptops, the pipe operator, and then filter, I'll give in these two conditions. So the first condition is company needs to be equal to Dell, and after that I'll give in the AND operator, and then I'll give in the second condition, which is inches needs to be greater than 15. I'll store this in laptops Dell 15 inch. Right, so we have this column over here, company, and the company's Dell, and we've got the inches column, and we see that the inches is greater than 15. So there are 215 laptops where the company is Dell and the inches is greater than 15. Now we can also combine the select function and the filter function together. So when we combine these two, we can only select those columns which we want and only those records which we want. So let's perform this operation over here. So this is the first operation where I am extracting only the company column, the product column, and the price in euros column. And I am filtering out only those records where the company name is Dell. And I'm storing it in laptop final. So I'm just extracting 3 columns and only those records where the company name is Dell. So view of laptop final. Right, I've got only these 3 columns and I've got only those records where the company name is Dell. So let's understand this code in a better way. First, I'll give in the name of the data frame, which is laptops, and then I'll use the pipe operator. So with the help of this pipe operator, I am combining this laptops data frame and the select function. After that, I'll again give in the pipe operator and then I'll give in the filter function. So I am joining this laptops data frame with the select function and the filter function, and the final result is stored in laptop final. Now similarly, let me give in another condition. So this time I am selecting only the company column, product column, CPU column, and the RAM column, and I'm filtering out those records where the company name is Lenovo and the RAM is 4 GB, and I'm storing it in laptop final 2. So I've got these 4 columns over here, and these 2 conditions have also been satisfied. So the name of the company is Lenovo and the RAM size is 4 GB. So there are 89 records or 89 Lenovo laptops whose RAM size is exactly 4 GB. So this is how we can perform different data manipulation operations using the dplyr package. Now we are on to the final part of this tutorial, where we'll understand about data visualization and how to implement data visualization operations with the ggplot2 package. So let's again take the same example where you're given a huge Excel sheet which has a lot of rows and a lot of columns. Now if you just look at the Excel sheet, you wouldn't be able to understand anything. But if you go ahead and make charts out of this Excel sheet, so let's say you make a bar plot or a histogram or a scatter plot for this Excel sheet, then you'd be able to interpret this data in a much better way. So this is exactly where data visualization comes in. So as I say, pictures speak more than words. And that is why data visualization is an extremely important part of the data analytics lifecycle. And to implement data visualization with R, we have this ggplot2 package. And again, ggplot2 is based on something known as grammar of data visualization. So as every language has grammar associated with it, and since visualization is also a form of language, even it has grammar associated with it. So to simply put, with the help of ggplot2, you can stack layers on top of each other. So first you start off with the data layer, where you basically choose what is the data you want to work upon. And on top of the data layer, you stack the aesthetics layer. So on the aesthetics layer, you basically map your columns onto different aesthetics. So you basically choose which column has to go onto the X aesthetic, which column has to go onto the Y aesthetic, and which column basically determines the color of these plots. Now, once you have the data layer and the aesthetics layer ready, then you have the geometry layer, where you go ahead and build some geometries. Now, these geometries are basically the plots which you build. So let's say you have a histogram, a scatter plot, a box plot, or a scatter plot, then all of these are the geometries. So first you start with the data layer, then you get to the aesthetics layer, and then you get to the geometry layer. So these are some of the basics of grammar of data visualization. Now let's go back to RStudio and perform some data visualization with the ggplotter package. So our first task would be to load up the ggplotter library. I'll type in library of ggplot2. And before again loading a library, we'd have to install it. So I'll click on this install tab, and then you just have to give in the name of the package, which is ggplot2. And when you click on install, the package would be installed. And we'll be implementing all of these visualization operations on top of the diamonds dataset. So view of diamonds, and we've got this dataset over here. Now let me check the number of columns and rows present in it. So ncol of diamonds. So there are 10 columns in this data frame. Let me check the number of rows. So n row of diamonds. And there are 53,940 rows in this diamonds dataset. Now let's understand about this dataset. So I'll just put in a question mark and I'll type in diamonds over here. So we see that this is a dataset which basically comprises of the prices and other attributes of almost 54,000 diamonds. And these are the different variables we have. So we've got the price column over here. So this is basically the price of the diamond in US dollars. And then we've got carat, which tells us the weight of the diamond, and it ranges from 0.2 to 5.01. Then we've got the cut of the diamond, which tells about the quality of the cut. So these are all the different levels which are present: fair, good, very good, premium, and ideal. Then we've got the color. So the diamond color varies from J to D, J being the worst and D being the best. And then we've got the clarity of the diamond. So clarity of the diamond is basically a measurement of how clear the diamond is. So L1 being the worst and IF being the best. Then we've got X, Y, and Z. So X, Y, and Z over here. X is basically the length of the diamond in millimeters, Y is the width of the diamond in millimeters, and Z is the depth of the diamond in millimeters. And finally, we've got the depth and the table columns over here. So depth is the total depth. So depth is the total depth percentage, and table is the width of the top of the diamond related to the widest point. So this is some of the description of the data set. Now let's go ahead and build some beautiful plots on this data set. So we'll start off by making a histogram. So with the help of a histogram, we can do univariate analysis. So what we'll do is, so what exactly is a histogram? So with the help of a histogram, we can do univariate analysis. So by univariate analysis, I mean that we can understand one particular column. And with the help of histogram, we can understand the distribution of a continuous column. So we've got these continuous columns over here: depth, table, price, X, Y, and Z. Now I'm going to go ahead and make a histogram for the price column, and this is how I'll do it. So this is the syntax for it. So ggplot, and inside this I'll give in the name of the data, which is diamonds, and then I'll map the price column onto the X aesthetic, and then I'll fit in the geometry, which is geom histogram. So I have successfully made a histogram for this price column. Now this syntax might seem too much, so let me actually break it down. So as I've told you, with the help of ggplot, you can add stacks on each other. So you'll start off with the ggplot command, and then you will give in the data layer. So you'll type in data, and then the data which you're working with is basically the diamonds data set. So you have chosen your data set, which is diamonds. I'll click on enter. Right. So you have basically started with your data layer, right? So this would be at the bottom. Now after this, you will choose your aesthetics. So you'll type in AES. And then I want to map the price column onto the X aesthetic. So I'll type in price, and I'm mapping this onto the X aesthetic. I'll hit enter. So I have successfully mapped the price column onto the X aesthetic over here. So you see that the price ranges from 0 and it goes on till about 50,000 over here. So we've mapped price onto the X aesthetic. Now it's time for the geometry layer. So now after the data layer and the aesthetic layer, if we have to add any more layers, we will use the plus operator and then add new layers. Now I want to add a geometry layer on top of this, and the geometry which I want to use is a histogram. So to build a histogram, we've got the geom histogram function. So geom histogram, and I'll hit enter. So now I've got everything. I've got the data layer, which is the diamonds, and then I've mapped the price onto the X aesthetic, and then the geometry which is used by me is geom histogram. Let me zoom this now. So this is a very beautiful picture, isn't it? And this shows the distribution of the price of the diamonds dataset. So if we have a glance at it carefully, we see that there are around more than 12,000 diamonds whose price would be not even 2,500 euros. And then when we come over here, so this is the price range of 5,000 euros. So there would be around 2,500 diamonds whose price would be 5,000 euros. Then we come over here. So this is the 10,000 price bracket. And this bar over here is again very, very small. So there would be not even around 100 or 200 diamonds whose price is 10,000. And when you come at this far end over here, right? So this is the smallest bar over here. So this would be the price of those diamonds whose value is greater than 18,000. So there are very, very few diamonds whose price is greater than 18,000. And these are some of the inferences which you can make with this histogram. Now let's go ahead and add some color to this. So this is the histogram which we have. Now inside this histogram, I want to add some color to this. To add the color, I would just have to use the fill attribute inside this geom histogram function. And the color which I want to add is green. Right, so I have successfully added the green color to all of the bars of this histogram. So this is the fill color. Now I can actually add a boundary color to all of the bins. And to add a boundary color, I have the COL attribute. And I'll set the boundary color to be equal to orange. Right, so I have added the fill color which is green and the boundary color which is orange. Now going ahead, we'll build a bar plot with the help of which we'll understand the distribution of a categorical column. So this is basically the difference between a histogram and a bar plot. So histogram is basically used to understand the distribution of a continuous valued variable, and a bar plot is used to understand the distribution of a categorical variable. Now we'll be building a bar plot on top of this cut column. So because we've got all of these different categories over here, and I want to understand the distribution of each of these categories. So again, I would follow the same procedure. I'll start off with using the ggplot function, and then inside this, I'll map the diamonds dataset onto the data layer, and then I'll use the aesthetic, and then I'll map the cut onto the X aesthetic. Then I'll add the geometry layer. And the geometry which we'd want to use is geom bar. So this is the bar plot which we've built for this cut column. I'll zoom this. So we see that there are more than 20,000 diamonds which have the ideal cut. And there would be not even 2,000 diamonds whose cut is ideal. And we've got around 12,500 diamonds whose cut is very good. And we've got around 13 to 14,000 diamonds whose cut is premium. Right, so obviously it's very easy when we actually build a plot. So now with the help of this graph, you can actually understand that visualization makes it very easy to understand the data. Now, if you are just looking at the data set, so let me open this data set over here, right? And if you just look at this cut column, then you would not have been able to understand this particular distribution over here. So with just one line of command, I was able to understand the distribution of this cut column. Now, similarly, let me make it more beautiful over here. So I'll add the color to this, and the color which I'll be adding to this is pale green 4. So I'll type in pale green 4 over here. I've added this fill color. Now, if I actually want the color of these bars to be determined by a column, then I can map a column onto the fill aesthetic. And over here, that is what I'm doing. So I have mapped the cut column onto the X aesthetic, and then I am mapping the same cut column onto the fill aesthetic. So this means that the fill color of these bars would be determined by the cut column. So this is the only difference. I'm using fill as an aesthetic rather than as an attribute. So if I put in the value of fill inside geom bar, then it will be taken as an attribute. But if I put in fill inside this aesthetic function, then it will be taken as an aesthetic. So now you see that each of these color is being determined by the different levels of this cut column, right? So fair column is denoted with purple, then we've got good, very good, premium is denoted with green, and then we've got the ideal bar which is denoted with the yellow color. So this was a histogram and a bar plot. Now let's go ahead and create a scatter plot. So with the scatter plot, we can understand the distribution between two numeric columns. So how does one numeric column vary with another numeric column? And over here, we are trying to understand how does the price of diamond vary with respect to the carat value. So let me type this out first. So I'll type in ggplot, and I will map in the diamonds layer onto the data aesthetic. And then I'll use the aesthetic layer, and I'll map the price column onto the Y aesthetic. Then I will basically map the caret column onto the x aesthetic. And then since I have to create a scatter plot, I'll be using this geom point function. So this is our plot. We've got price mapped onto the y-axis and caret mapped onto the x-axis. So we see that the caret ranges from 0 to 5 and the price it ranges from 0 to around 18,000. And the inference is sort of clear. So as the caret value increases, the price of the diamond also increases. So this dot which you see, so this basically represents a diamond whose caret value is around 5 and the price of the diamond would be around $18,000. Then we've got this diamond over here again. So the caret value would be 4.5 and the price would be again around $18,000. Then we've got this diamond over here. So the caret value would be around 2.75 and the price of the diamond would be around 7,000 something, right? And we see that there is a greater distribution of diamonds over here. So throughout this data set, there are a lot of diamonds whose caret value ranges between 0 and 1 and their price ranges between 0 to 5,000. There is a greater density over here. And as we go to the right side of the graph, the density decreases. So there are very few diamonds whose price would be, let's say, greater than 12,500 and whose caret value is greater than 3. So you can actually count on your fingers the number of diamonds whose caret value is greater than 3. Now I'll go ahead and map the cut column onto the color aesthetic. So basically the color of all of these points would be determined by the cut column. Right, so the only difference is the color of the points is being determined by this cut column. So if you have a glance at these two diamonds, you see that the cut of these diamonds is fair. And you got a greater distribution of diamonds over here with the color yellow and green, right? So this bracket of the caret value being 0 and 1 and the price between 0 and 5,000, you see that there is a huge density of diamonds where the cut is ideal and premium. And you just did one minor change, which was adding this cut column onto the color aesthetic. Now we'll go on to the next type of geometry, which is box plot. So in box plot, we try to understand how does a numeric value change with a categorical value. And in this example, we are trying to understand how does the caret value of a diamond change with the clarity of a diamond. So again, the diamonds dataset has been mapped to the data layer. Then we've mapped the clarity column onto the X aesthetic and the caret column onto the Y aesthetic. And we're making a box plot for this. So the function to be used to make a box plot is geom box plot. And this is the plot which we have. So let me zoom this. So this is how a box plot looks like. Now let me explain these three lines over here. So this is the median line or the 50 percentile line. This is the 25 percentile line and this is the 75 percentile line. So if this median line tells you that if the clarity of the diamond is L1, then the caret value would be somewhere around 1.1 or 1.2. Similarly, if we take this particular box plot over here, this tells you that if the clarity of the diamond is IF, then the median caret value would be somewhere around 0.7 or 0.6. And all these dots which you see, so these are basically outliers. So this is basically one such outlier where the caret value is 5. So if you look at the general range of this caret value, then it would be around 0.2 or 0.3 over here, ranging to 2.2 or 2.3 over here. And all of these points which are about this line, all of these are outliers or anomalies. Now let me go ahead and add a color to these box plot on the basis of the clarity column. So I'm just making one minor change over here. So I am assigning the clarity column onto the fill aesthetic. So now each of these different box plots would have a different color. Now again, let me do something different. So now what I'll do is I will map the cut column onto the fill aesthetic. So now I've got caret onto the y-axis, clarity on the x-axis, and the color of these box plots is basically being determined by the cut column. And since the cut has all of these different levels, so we've got 5 different levels in the cut column, and for all of these different levels, we've got a different box plot. So this box plot is basically for that particular diamond where the clarity is L1 and the cut is fair. Then we have this box plot over here, which is for that diamond where the clarity is L1 and the cut is ideal. So let's draw some inferences from this graph. So if we take this box plot over here, then we can infer that there is a diamond where the clarity is L1 and the cut is fair. Then it would have the maximum caret value of 5. Now similarly, let's take this box plot over here. So the clarity is IF and the cut is ideal. then this would have a maximum caret value of around 2.2 or 2.3. So you can draw different types of inferences from this particular graph. Now we'll head on to the final part of this visualization, which is basically faceting. So if you actually look at this graph, then there are a lot of things which have been infused into one single plot. So what we'll do is we'll divide this one single plot into multiple plots on the basis of one column or multiple columns. And over here we are faceting or dividing this plot on the basis of the cut column. So there would be one subplot for the different types of cuts. So I am adding a new function over here, which is basically the facet grid column. And inside this, I'll give in the tilde symbol, and then I'll give in the name of the column on the basis of which these facets have to be made. So now we see that we've got 5 facets corresponding to the 5 different cuts. So this facet is for the cut value of fair. This is for good, very good, premium, and ideal. So one particular inference could be, so if you take L1 and fair, then we have the maximum caret value over here. Similarly, if you take the clarity to be VS2, then the maximum caret value would be for this diamond of the cut premium, right? Since this belongs to the premium cut. So again, when we facet our data, drawing inferences from this graph becomes extremely easy. Now we'll do one final thing when it comes to visualization. We'll see how to add themes to our plots. So we can actually add a theme to the panel and this particular plot. So I have the same command over here, and on this I'll add one more layer, which is basically the theme layer. And inside this theme layer, I would basically want to add a color to this particular plot. So I will type plot dot background equals, and then I've got different element functions over here. So if I want to make some change to a particular rectangle over here, right? So this plot is nothing but a rectangle. So I will select the element rect function, and inside this I will type in the fill attribute, and I want to add a color of, let's say, pale green 4 to this again. So I'll type in pale green 4. So I have successfully added this background color to this plot. Now this looks even more beautiful, doesn't it? Right? So this is how we can add a theme to our entire plot.
Now that we have learned all the basics of R programming, let's go ahead and work on a case study. So we'll be working on this Pokemon data set, and on this Pokemon data set, we'll be applying different data manipulation and data visualization operations. So our first task would be to load this data set, and to load this data set, we would have to use the read.csv function. So this is the command to load a file. So read.csv, and inside this I am giving the path of the file. So this is the path of the file, and I am storing it in a new object called as Pokemon over here. Now let me just have a glance at the data set which I've just read. So I'll use the view method, and inside this I will pass in the name of the data frame. So the name of the data frame would be Pokemon, and let's see what do we have over here. So these are the different columns which are present. So we've got abilities, we've got against bug, against dark, against dragon. So these columns are basically how does the Pokemon perform against these primary types. So let's say if this is the Pokemon, I'm trying to understand how would this particular Pokemon fight against the bug type Pokemon, or how well can it fight against a bug type Pokemon. Similarly over here, if we take this, how well can this Pokemon fight against a dragon type Pokemon? Similarly, this will tell us how well can a Pokemon fight against a fairy type Pokemon. Then we have other columns. Let's go ahead and look at other columns. We've got the attack rating of the Pokemon. We've got the base X steps, the base happiness. We've got the capture rate, classification, what exactly, what class do the Pokemon belong to. And then we have the defense of the Pokemon. Then we have the experience growth. After that, we have the height of the Pokemon and the weight of the Pokemon over here. We've got height in meters. And then we have the HP. You can consider HP to be sort of the strength of the Pokemon over here. And we've got the name of the Pokemon. This is the Japanese name. This is the name of the Pokemon. And we've got special attack, special defense, speed. Then we have type 1 and type 2. So type 1 over here would tell us the primary type of the Pokemon, and type 2 would tell us the secondary type of the Pokemon. So when we consider type 1 and type 2, this basically tells us that this is a grass poison sort of Pokemon. So primary type is grass and secondary type is poison. This means that primarily it is a grass Pokemon, but also it has some features of a poison Pokemon. And then we've got the weight column over here. Then we've got the generation column. This tells us to which generation does this Pokemon actually belong to. And we finally have the is legendary column. So this is legendary column would tell us if the Pokemon is a legendary Pokemon or not. So these are the different columns which are present in this data frame. Now let's go ahead and check how many rows and how many columns are present in this data frame. To check the number of rows, I would have to use the n row method. So I'll just type in n row, and inside this I will pass in the name of the data frame, which is Pokemon. And as we see, there are 801 rows in this data frame. Similarly, let me go ahead and check number of columns present. So I'll use the ncol method, and I will pass in the Pokemon data frame again. So now we get that there are 41 columns present. So in total, this is basically a data frame which has 801 rows and 41 columns. So now that this is clear, let's go ahead and do some observation with respect to the categorical columns. So categorical columns are basically which have categories in it, which are not continuous. So we've got these three categorical columns. So we've got S legendary, generation, and type 1. And I am basically building a tabulation of the S legendary column. That is, I'd want to understand the frequency of different levels which are present in the S legendary column. So I'll just type in table, and inside this, first I'd have to type in the name of the data frame, which is Pokemon. I'll use the dollar symbol and select the column. So the column which I'd want to select would be is legendary. So 0 over here would tell us that the Pokemon is not legendary, and 1 would tell us that the Pokemon is legendary. So out of the 801 Pokemons which we have, 731 are not legendary, and only 70 of those Pokemons are actually legendary. Now similarly, let's go ahead and make a tabulation of the generation column. So I'll use table. First I'll pass in the Pokemon data frame. I'll use the dollar symbol, and then I'll select the column. So column over here would be generation. And as we see, we have 7 generations in total. And this is the maximum value. So the maximum Pokemons belong to the 5th generation. So 156 Pokemons belong to the 5th generation. And then the minimum value is for the 6th generation over here. So there are only 72 Pokemons which belong to the 6th generation. So this is quite an interesting observation, isn't it? So we have got to see the different or the number of Pokemons belonging to each generation over here. Similarly, I'd want to see the number of Pokemons belonging to each primary type. So I'll use table function over here again, and first I'd have to use the name of the data frame, which is Pokemon. I'll use the dollar symbol, and then I'll just select type 1, which is the primary type. So these are the different primary types. We've got bug, dark, dragon, electric, fairy, fighting, and so on. So as a kid, if you had watched Pokemon, or even if you are an adult, well, Pokemon was a very good series. So there's nothing wrong in watching Pokemon even right now. So you would know that these are the different primary types which are present in a Pokemon. Now that we know all of this, let's draw some inferences. So we see that the majority of the Pokemons belong to water type. So there are 114 Pokemons belonging to water type. Now, let's say similarly, we've got the steel type Pokemons. There are only 24 steel type Pokemons. The least seems to be of the flying type. There are only 3 flying type Pokemons. That is very, very less, isn't it? And if we talk about fairy, there are 18 fairy type Pokemons. So again, a very interesting observation over here. So now that we've looked at some categorical columns, let's do some inference on the numerical columns over here. So we had the HP column in the data frame. Let me just go ahead and show you guys the HP column. So let me just see. So here is the HP column. Now I'd want to find out the minimum value and the maximum value of HP. That is, there would be some Pokemon which would have the minimum HP value, and there would be some Pokemon which would have the maximum HP value. And I would want to understand what exactly are those HP values. So I just have to use the min method over here. And inside this, again, I'll just have to pass in the column. So Pokemon, I'd have to use a dollar symbol, and the column would be HP. So the minimum HP value seems to be of 1. Now similarly, let's check the maximum HP value. I'll use maximum, and again I'll use Pokemon dollar, and I would have to use the HP column again. And as we see, the maximum HP of a Pokemon is 255. That's quite interesting, isn't it? So minimum value is only 1 and the maximum is 255. So there's a huge difference between the minimum value and the maximum value over here. Now, similarly, I'd want to find out what is the minimum value of the speed of a Pokemon and what is the maximum value of the speed of the Pokemon. I'll just use min over here. And inside this, I'll pass in the name of the Pokemon of the data frame, which is Pokemon $, and the column is speed, right? So it seems that there is one particular Pokemon whose speed is 5, and that is the minimum value of speed that can be possible. Similarly, I'll use max over here, and I'll give in the name of the data frame, which is Pokemon, and I'll select the column, which is speed. And we see that there is one particular Pokemon whose speed is 180, and that is the maximum speed possible. Right, so we've looked at these as well. Now we'll see if there are any missing values present in the data frame. To check if there are any missing values, we'd have to use the is.na method. So is.na tells us if there are any na values or missing values. So I'll just use is.na, and let's say I'd want to check this for the abilities column. So is.na Pokemon $abilities. Now, as you see, we have a bunch of false values over here. So normally we will get a bunch of true or false values. So those bunch of true or false values would tell you. So let's say if there's a false value, that would mean that there is no NA. That is, the value is present. But on the contrary, if the value is true over here, so if you see any true, that would mean a NA is present over there. But as we scroll through all of these values, we see that all of them are false values and there are no NA values over here. So just to verify it, I can just sum up all of the values. So I would just have to use sum, and inside this I'll pass in is.na, and inside this let me just pass in the abilities column again. So I'll pass Pokemon $abilities, and as we see it is 0. So there are 0 NA values present in the abilities column. So this is done. Now we'd have to rename some columns. So type 1 and type 2 are not really intuitive. So I'd have to rename the column from type 1 to primary type. So first I'd have to use call names. So this is the command which I'm writing over here. So I'll just go ahead and type call names. And when I type in the name of the data frame over here, let's see what do we get. So inside the call names method, when I pass in the name of the data frame, I just get a bunch of all of the columns which I have, right? So as you see, these are the 41 columns which are present. So I get the list of all of the names. Now, similarly, what I'll do is call names of Pokemon is equal to, I'll just pass in type 1. And when I do this, let's see what do we get. So you have a bunch of true and false again. So you have all of the false, you have true over here. So this true indicates, so now when you say call names of Pokemon, you get all of the column names of this data frame. And I want to check wherever the column name in this data frame is equal to type 1. And it seems that at this particular position, the name of the column is equal to type 1. So with this command, what I'm doing is out of all of the column names, wherever the column name is equal to type 1, I'd want to change that column name to primary type. Right, so I hope this is clear to all of you guys. So let me write the entire command over here, call names. Inside this, first I'd have to pass in the name of the data frame. Then again, I'd have to use this parenthesis. So this parenthesis, inside this, I'll get a bunch of true and false values. So I'll use call names over here and I'll pass in the name of the data frame again. And I'll use double equal to operator and I'll set the column name to be equal to type 1. So this will give me a bunch of true and false values, and those bunch of true and false values I'm storing in this parenthesis. That would mean that wherever out of these values I have a true, in that case, I will go ahead and change it to primary type. So let me go ahead and change it to primary type. Right, now let me have a glance at this data frame view of Pokemon and let's see if we've made the necessary changes. Let me go to the end of this. So as you see, initially the name of this column was type 1 and we have successfully changed this to primary type. Now similarly, let's go ahead and change the column name of type 2 to secondary type. So we'd have to use a similar command over here. So I'd have to give in call names. Inside this, I'll pass in the name of the data frame, which is Pokemon. I'll give in parenthesis over here. again call names inside this name of the data frame, which is Pokemon, and this time I am checking if the column name is equal to type 2. And if the column name is equal to type 2, I'd want to change it to secondary type. Now I'll go ahead and have a glance at the modified data frame again, just to verify if the changes have been done or not. Let me just drag this to the end and let's see what do we have. So as you see, initially this was named type 2 and we were able to change the name of the column from type 2 to secondary type. This is done as well. Now we will also go ahead and change the name of the column of this. What you see, we have a column called name and I'd want to change that to Pokemon name. That is also very simple. We'd have to perform a similar command over here. We'd have to use call names. Inside this, I'd have to pass in the name of the data frame, which is Pokemon. I have this parenthesis over here. I'll use call names. I'll pass in the name of the data frame, which is Pokemon over here. And I'll check if this value is equal to name. And if it is equal to name, I'll just go ahead and I'll change the name of the column to Pokemon name. View of Pokemon, and let's see what do we get over here. Let me go to, let's see if we can find it. So as you see, initially this column was called as name, just name, and we have changed it to Pokemon name. So this is how we can go ahead and change the name of a column as well. Right, so now that we've done all of this, we've done some basic pre-processing. We've looked at the different categorical columns. We've looked at some variation of the numerical columns. We've seen if there are any missing values, and we've also gone ahead and renamed some columns. Now it's time to do some data manipulation. So from this entire Pokemon data set, I'd want to extract only grass type Pokemons. That is, from the entire data frame, I'd want to select all the records where the primary type is equal to grass. So let me go ahead and write the command for that. So first I'd have to go in and give in the name of the data frame, which is Pokemon. Then I'd have to use the pipe operator. So I'll give in pipe and I'll use the filter function. So this filter function is actually part of the dplyr package. So before writing this command, I'd have to load the dplyr package. I'll write library of dplyr. Now that we've loaded this, let me go ahead with the command. Pokemon is the data frame. And from this Pokemon data frame, I am using the filter function so that I can extract all of those records where if the primary type is equal to grass. So with the help of this filter function, I'm giving the condition, and the condition is primary type of the Pokemon needs to be equal to grass. And wherever that condition is satisfied, or whichever records satisfy those condition, I will select all of those records and I will store them in an object called as grass Pokemon. Now let me have a glance at this new object called as grass Pokemon, and let's see what do we get over here. Let me go to the primary type column. So as you see, we have all of these different entries, and if you look at the records over here, all of them are grass. So as you see, all of them are just grass over here. Right. So we have done this as well. Now that we have created this new object called as grass Pokemon, I'd want to analyze some features of this grass Pokemon which I've just created. So I'd want to find out the minimum speed of a grass Pokemon. So I'll use the minimum method. So we already work with this. And now the name of the data frame would be grass Pokemon. I'll use the dollar symbol and the name of the column would be speed. So as you see, the minimum speed of a grass type Pokemon seems to be 10. Now let's go ahead and also check the maximum speed of a grass type Pokemon. I'll use the max method over here. And inside this, again, I'd have to pass in the name of the data frame, which is grass Pokemon, and I'd have to select the column. So the name of the column would be speed. So it seems that the maximum speed of a grass type Pokemon is 145. So I'll just go ahead and add a comment over here so that I can compare it with the other type of Pokemons which we'll be extracting later. So minimum speed value of a grass type Pokemon is 10, and similarly the maximum speed value of a grass type Pokemon is 145. So this was the minimum and maximum value of speed. Now, similarly, let's go ahead and find out the mean value of special attack and special defense for a grass type Pokemon. So I'd have to use the mean method and the data frame would be grass Pokemon. I'd have to select the column. So first I'd want to find out the mean of special attack. So it seems that on an average, a grass Pokemon would have a special attack of 74. So similarly, let me find out the average value of special defense. So I'll use mean over here. Again, grass Pokemon. And this time I'd want to find out the average of special defense. So it seems that on an average, the value of special defense for a grass Pokemon seems to be 69. So again, I'll add a comment over here. Again, I'll use hash and the special attack is 74. And similarly, I'll use hash over here and the special defense is 69. Right, so I have done some basic inference over here. Now I'll go ahead and make some plots on this grass type Pokemon. So to make some plots, we'd have to use the ggplot2 library. I'll just type in library and load the package. So the name of the package is ggplot2. We have loaded this. Now I'd want to understand the distribution of HP for a grass type Pokemon. So first I'd have to use the function ggplot. I'd have to map the data frame onto the data aesthetic. I'll use data over here. I'll be mapping the grass Pokemon onto the data aesthetic over here or the data layer over here. And I will use the aesthetic. And inside aesthetic, I will just be mapping HP onto the X aesthetic. So I have HP and I'm mapping HP onto the X aesthetic. And the distribution or the plot which I want to make right now is geom histogram. So let me just go ahead and write in the name of the method, which is geom histogram. So this is what we get over here. So it seems that this is the maximum value. So this would be around, let's say we call it around 60. So this value of 60 or 65. So there are around 12 Pokemons. You can say there are around 12 Pokemons whose HP is 60. Similarly, if we take this, it seems that there is just one Pokemon whose HP is close to 120. If we take this value over here, there is only one grass type Pokemon whose value is very low. It is around 20, it's somewhere between 25 to 30 if we can say. And again, if we take this bar over here, so there are around 10 Pokemons whose HP is equal to 75. So again, these are some sort of inferences which we were able to make with the help of this histogram. Now I'd want to go ahead and add some color to this. To add a color, I'll be just using the fill attribute over here. So I'll just use fill. And inside this, I will pass in the name of the color, which is pale green 4. So as you guys see, we were successfully able to add color to this particular histogram over here. Now, similarly, we will go ahead and make a histogram for the height of the grass type Pokemon. So I'd want to understand what is the variation in the height of the grass type Pokemons. So again, ggplot, and I'll be mapping the Pokemon data frame onto the data layer because that is the data which I'm working with. And I'll start with the aesthetic layer. I'd have to map the height onto the X aesthetic. So the name of the column is height M, and again the geometry used by me is geom histogram. So I'll just type in geom histogram over here and let's see what do we get. Let me zoom this over here. So as you see, most of the Pokemons, so there are more than let's say 250 Pokemons whose height is very, very less. So their height would be somewhere around, let's say 1.5 or 2 meters. So seems that the grass type Pokemons are not very tall. And there is just one Pokemon whose height is close to around 14 meters or 13 meters. And over here, let's say you have around 2 Pokemons whose height is around 9 meters. And you have around one Pokemon whose height is 8 or 7.5 meters over here. Right. So this basically tells you most of the Pokemons, their height would be somewhere between 1 to 2 meters if they are of grass type. An interesting observation over here. Similarly, I'd want to understand the distribution of the weight of these grass type Pokemons. So again, ggplot, and onto the data layer, I'll be mapping the Pokemon data frame, aesthetic layer again, and onto the x-axis. This time I'd have to map the weight column. So I'll just type in weight kg over here, and the Geometry used by me is again geom histogram. So let me just type in geom histogram and I'll give it a color. So let's say the color which is given by me is coral. So seems like we have an error over here. Mapping must be created. Weight kg. So let me just go ahead and check what is this error over here. Data is, have I given this equal to properly? This seems to be fine. Aesthetic weight is kg. Let me make this capital kg. Let's see what is the error over here. So let me just go ahead and write the command again. So I'll just type ggplot over here and data would be grass Pokemon. So let me just pass in the data over here. I'd have to use the aesthetic. So over here onto the x-axis, I'd have to pass in the weight. So this will be weight in kg. And I'd have to use a geometry now. The geometry will be geom histogram. Let me just use geom histogram over here. So you have successfully created this. Let me go ahead and add the color, which is coral. So this was the mistake which you had did. So we just had to use the fill attribute. So fill is equal to coral. Right, so as you see, we have successfully assigned this color called as coral to this particular graph over here. And as we see for most of the Pokemon, so if it is grass type, there are around 25 Pokemons whose weight would be, let's say, around 10 kgs over here maybe. And there are around 5 Pokemons whose weight is would be around close to 100 kgs or exactly 100 kgs. And there is one Pokemon whose weight is 200 kgs. And there is one Pokemon again whose weight is more than 300 kgs. So again, interesting observations over here, which we get from this. So now that we've done this, what I'd want to do is I'd want to understand how many legendary Pokemons are there when it comes to the grass type Pokemons. So for this, I'll be making a bar plot. So ggplot, and I'll just use data over here. And again, I'll map the grass Pokemon onto the data layer. And inside aesthetic, I would have to map the S legendary column onto the x-axis. Let me give in the name of the column, which is S legendary, and the geometry used by me is geom bar. So I'll just use geom bar over here and I'll give it a color. So let's say the color which I'll give over here this time is blue. Right, so as we see over here, there are very, very few legendary Pokemons when it comes to grass type. But when it comes to non-legendary, so as you see, there are, or you can say most or 95% or even 98% of the Pokemons are not legendary when they are of grass type. So this count would be, let's say, around 3 or 4 or even less than that. So there are very, very few Pokemons who are actually legendary when it comes to grass type. Right, so this was an interesting observation again. So as we had extracted all of the grass type Pokemon, similarly, we will go ahead and extract all of the fire type Pokemons. So first I'll have to give in the name of the data frame, which is Pokemon. I'll use the pipe operator, and using the pipe operator, I'll use the filter method. So from this Pokemon data frame, now I'd have to give in a condition. So the condition is wherever the primary type is equal to fire, I'd want to extract all of those Pokemons. And once I extract them, I will store that in an object called as fire Pokemon. Now let me have a glance at this, which I've just created. So view of fire Pokemon. Let me see what I have over here. Let me go to the primary type. So as you see, we have 52 entries, and out of these 52 entries, when we look at the primary type column, all of them are fire type. So we have successfully extracted all of the fire type Pokemons from this entire data frame. Now I'd want to find out the minimum and maximum speed of the fire type Pokemons to compare the speed with the grass type. So I'll use the min method. I'll use the name of the data frame, which is fire Pokemon, and select the column, which is speed. So it seems that the minimum speed of a fire type Pokemon is 20. So let me add 20 over here. Now let me go ahead and compare it to the grass type. So it seems that the minimum speed of a grass type Pokemon is 10, but the minimum speed of a fire type Pokemon is 20. So this is an interesting observation. Similarly, let me go ahead and also find out the maximum speed. So I'll just use the max method over here, and it seems that the maximum speed of a fire type Pokemon is 126. So let me go up over here. So when it comes to grass type, it is 145. So there is one grass type Pokemon whose speed is 145. But when it compared to fire type Pokemon, seems that we don't have any fire Pokemon whose speed is close to 145 or above that. So let me add a comment over here. So the maximum speed of a fire type Pokemon is 126. Now that we have done this, I'd also want to look at the mean special attack and mean special defense. Mean of, and name of the data frame is fire Pokemon. I'd want to find out the SP attack. So it is 87. Let me just add 87 over here. And also let me go ahead and check the special defense. So mean of fire Pokemon, I will just make it special defense over here, and the value of this is 71. So let me make it 71 over here. So let me compare it with grass type again. So average special attack and special defense is 87 and 71. So when I compare it with grass type, so it seems that fire type Pokemon has a higher, or on an average, fire type Pokemons have their special attack and special defense to be higher than grass type Pokemons. So this is again very interesting to know over here. So now that we've done this, we would have to go ahead and visualize some patterns when it comes to fire Pokemons. And for that purpose, I'd have to use the ggplot library. So I'll use ggplot, and this time what I'd want to do is I'd want to understand how many of the Pokemons belong to different generations. So what is the frequency of the fire type Pokemons with respect to generations? So ggplot data, and I'm mapping the fire Pokemon onto the data layer. Then I have the aesthetic layer, and I am mapping the generation column onto the aesthetic layer on the X aesthetic actually. So I'll just set generation is equal to X. Then I'd have to set the fill as well. So I'll set fill is equal to as dot factor, and inside this I will pass in the name of the column, which is generation. That is, I'd want the color of all of the bars to be determined by the generation column over here, and obviously the geometry which is being used by me is geom bar. So I just use geom bar over here, and let me hit on enter, and let's see what do we get. So as you see, we have 7 generations of fire type Pokemons, or in general there are 7 generations. And so most of the fire type Pokemons, they belong to generation 1. So there are around 11 Pokemons who belong to generation 1, and it seems that this is the minimum value over here. So there are only 4 fire type Pokemons which belong to generation 4 over here. There are only 5 fire type Pokemons which belong to generation 4. Similarly, if we take this, there are only 5 fire type Pokemons which belong to generation 7. So this we were able to understand by building a bar plot. Now let's see what is the next type of visualization which we'd have to make. So now we'd want to understand what are the different secondary types for the fire type Pokemon over here. So ggplot, and onto the data layer I'll be mapping the fire Pokemon, and I'll be using aesthetic over here, and I'll be mapping the secondary type onto the X aesthetic. Let me just use secondary type over here. I'm mapping secondary type onto the X aesthetic, and then I'll use fill. So again, basically the color of the bars would be determined by the secondary type column. So I'll set the fill to be equal to secondary type as well. And once that this is done, all I have to use is make a bar plot. So let me just use the geometry, which would be equal to geom bar. And this is what we have over here. Let me go ahead and add a color. So as you see over here, so fill, it has to be, I'll just make it as dot factor over here. And let me pass it inside as dot factor. Let me cut it. Let me paste it over here. Now let me run this. So we'd have to put this inside the aesthetic layers. So that is what the error is over here. Let me cut this entire thing from over here, and let me paste it inside this. And now let's go ahead and click on run, and let's see the result. Right. So as we see, these are the different secondary types for a fire type Pokemon. And it seems that so this is basically we don't have a value over here. So it seems that they are like genuinely fire Pokemons and they don't have any secondary type. So after that, if we look at these two, so this basically indicates flying type. So there are so the majorities of those fire type pokemons whose secondary type is flying, and then similarly it seems that most of the fire type pokemons can also be fighting type pokemons. Then we have these three, so we have ground, ice, and normal. Then the next are like very very small. It seems like there is only one pokemon, so it seems like there is only one or two pokemons whose primary type is fire and whose secondary type is steel and water. So this is actually very intuitive, isn't it? So you can't really have a Pokemon whose primary type is fire and whose secondary type is water. So that doesn't really seem to be possible. Right, so now that we have done this, let's go ahead and make another visualization where we are trying to understand what is the difference between the special attack and special defense of the fire type Pokemon. So for this purpose, we'll be making a scatter plot. So let me type in ggplot over here and I'll be mapping fire Pokemon onto the data. Let me use the aesthetic layer now and I'll be mapping special attack onto the x-axis. Let me just type in SP attack over here, and then onto the y-axis, I'll be mapping SP defense. Now let me go ahead and use the geometry. So the geometry which I'll be using now is geom point, and let's see what do we get. So it sort of seems like there's a linear relationship, if you can call it. So if the special attack of the Pokemon increases, the special defense of the fire Pokemon would also increase. Right, so sort of an interesting observation over here, right? Or you can even put it this way. So if a fire type Pokemon has a high special attack, then it would also mean that the fire type Pokemon would, there's a greater probability for the fire type Pokemon to have a higher special defense as well. So this is sort of the inference which you can make from this. Now what we'll do is we will go ahead and make a plot of weight versus height. So again, we'd have to make a scatter plot. So ggplot onto the data, we'll have the fire Pokemon, and in the aesthetic layer, we'll have height m mapped onto the x-axis. So x would be equal to height m, and onto the y-axis, we'll be mapping the weight. So weight kg, and let me go ahead and use the geometry. So the geometry would be geom point. And let's see what do we get over here. So this is point, not point. Right. So again, sort of as you see, if the height is increasing, the weight is also increasing. But then again, you can't really say that this is a linear relationship. And if the height is more, the weight is also more. So you can't really say there is a direct relationship between height and weight. But sort of, you can say there is a slight probability that if the fire type Pokemon has a very good height, then it must also have very good weight. Right, so if you look at this over here, so it seems that the height of the Pokemon is very large, right? So it would be around, let's say, close to 4 meters would be the height of this fire type Pokemon over here, but the weight of the Pokemon is very low. Similarly, if we take this point over here, so again, this is an outlier where the height of the Pokemon would be, let's say, around 1.75 meters, and the weight of the Pokemon is more than 400 kgs, right? So we've got two outliers or anomalies over here, but this is the general trend. This general trend tells us that the height of a fire type Pokemon would normally range between 0 to 2 meters, and the weight would normally range between 0 to around 200 kgs. So interesting observation over here again.
So with neural networks, we'll start off with seeing briefly what a biological neural network is. We won't go into much of the details. We'll just do an overview because it helps to understand what an artificial neural network does. Then we'll see the overview of artificial neural network and a small example, a pretty small example on what happens and how a neural network learns. We'll see how we implement AAN and different steps that are a part of implementing artificial neural network. One of them being backpropagation, then the weights updation, and then the error function. Then we'll also see the summary of what the overall learning algorithm that the neural network follows. And then we'll see how we implement neural network in R using the same, using that same iris data set that we used to do, so that we only know what is the essence of using neural network in R, and we're able to compare the outputs of what we did with previous algorithms and what the neural network gives us. Okay. So with biological neural networks, you would have seen already how they're the basic building blocks of the the central nervous system. So these are the diagrams which may be repetitive for you, but then they help us understand what a biological neural network does. So not going very deep into biology. So something that you see in yellow is a neuron, okay, which is similar to a neuron in the artificial neural network, wherein each contains some data about the input data variables. Okay, so like the neurons are interconnected at the point called synapses. So in the diagram above, you see red circle where there is a synapse. So neurons are interconnected at the point called synapses, and this is similar to the artificial neural network because the different input variables that you take, that information is passed to the hidden layer, and how that information is passed to the hidden layers is through a point which is similar to the synapse in the biological neural network. So there are three parts that are typically present in a biological neural network. One is the dendrite, which is the yellow you can say like terminals of a neural network, which are responsible to receive signals from the surrounding neurons. Then there are axons, which are nothing like a path. So comparing it to the artificial neural network, like there is a path when you go from the input layer to the hidden layer. There is a path in between which carries the information. So the axon is similar to that. Then the synapses are responsible for receiving the signals and learning from the past activities. How we correlate it to the artificial neural network is because if you know of the concept of back propagation, even the artificial neural network learns from its past activities. Hence, you're able to kind of relate the biological neural network with the artificial neural network. So each of the neuron here acts as a neuron in the artificial neural network. The axons act as a path where the information is traversed from one layer of neural network to the another layer of the neural network. Then the dendrites and synapses are used to send and receive information between one neuron to the other, and then they also enable the neural network to learn from the past activities, and that's how the algorithm improves itself. Okay, so this is essential to understand only because the artificial neural network gets its name from the biological neural network only. Okay. So this is again a small diagram to just show you how the information is passed with the biological neural network, and a similar kind of thing happens with the artificial neural network as well. Okay, so what happens is whenever a certain information is coming to a neuron, when a certain information is present in a neuron, so there's this thing called threshold, which we're also seeing with the artificial neural network. So once that threshold is reached, when that threshold has been achieved, the neural network transmits a signal through the axon. And the similar kind of thing happens with the artificial neural network as well. Whenever the threshold is reached, activation function triggers, and then an information is passed from the input layer to the output layer. So we'll see how each of these steps in the biological neural network helps us also understand what is present in the artificial neural network. Okay, so this is how a basic of how an artificial neural network works. So the inputs that you see here are nothing but the input data variables with the data set they are working with. Then there are certain weights which are applied to each of the input variables. So the weights that are applied are nothing but they help the neural network to tell what is the importance of each of the variables. So this is also what we saw with the previous algorithms we learned. So each variable that is present in our input data set does not have equal importance. Okay, each input variable does not have equal importance. There are variables which are more important, there are variables which are lesser important. How that is decided is through these weights. So whichever variable is given a higher weight is comparatively more important than a variable which has a lesser weight. So this is how the weights are used in a neural network. So the set of inputs which are nothing but the variables from the data set are thought of as neurons. This is how we correlate an artificial neural network with a biological neural network. So then they are weighed according to the weights that are applied, what I just told. And finally, this is we do kind of a sum product of the input variables with the weights. Sum product means to say x1 into w1 plus x2 into w2 plus x3 into w3 and so on. Okay, so the function that you see here, the summation function or the sigma function here, this can also be called as a transfer function. So this actually performs the sum product. So it will sum up the weights and the input that it receives from each of the neuron. The next step is to go to the activation function, which will decide whether or not a neuron will fire. So this is similar to the biological neural network, wherein with the threshold, we decide whether or not the information should be sent to the next layer. Okay, so if the threshold, so whatever sum you get using the transfer function, you compare it to the threshold. If it exceeds the threshold, the activation function decides to fire. When it fires, the information is passed from the input layer to the output layer, like similar to what happens in the biological neural network. When the activation function fires, information is passed from one layer to the other. Okay, so like I told earlier also, the weights can be used to amplify or de-amplify the original input signal, meaning to say they are used to determine how each variable will be used, what is the importance that will be given to each of the variables. Okay, so consider a simple example. So this example has got nothing to do with the neural networks actually. Consider that you have just say two input variables x1 and x2. So these are two input variables in a data set, one of them having a value of 0.6 and one of them having a value of 1. And the weights say that are applied to both of these input variables are 0.5 and 0.8. Okay, and you've also been given a threshold of 1. So what happens in simple terms in the neural network is the first step of a transfer function, what we saw in the previous slide. So nothing but a sum product will happen here. So 0.6 into 0.5 plus 1 into 0.8. So that gives you a 1.1. So this is similar to the summation function that we had seen here. Next, we compare this value that we've got with the threshold. So say our value that we've got is 1.1, but the threshold is 1.0. So we see that our output is more than the threshold that was allowed. So since the output is greater than the threshold, so the neuron is activated and it fires. Okay, so this is a very simple example. This is not what actually happens in the neural network, because there a derivative of the error function and all that is calculated. So error function is nothing but the actual output, a difference between the actual output and the desired output. So therein a derivative of that is calculated and passed back to the neural network, but I put this example only to show you how the threshold works. So whenever the output exceeds the threshold, the neural network will know that it needs to fire a signal. What is meant by firing a signal is nothing but a back propagation, meaning to say that whenever an output increases the threshold, the algorithm will whenever the output increases the threshold, a back propagation will occur and a reiteration will occur, a new iteration within the neural network will occur, and the the algorithm will try to improve the output. Okay. Now we'll see how we implement the artificial neural network. So this is a simple diagram to show how a neural network works. So there are, for example, 3 input variables and 2 output variables here. So there can be any number of hidden layers that are present in the neural network, and the hidden layers actually perform whatever the algorithm needs to be applied is done by the hidden layers only. There are different ways on how we decide how many hidden layers are to be present, and we'll see that when we work with R. So what happens here is that the input layer will take the input from the input variables. So say you have 3 variables here. So each of the neuron that you see in the input layer will have data from 1 variable each. The input layer will take input from the input variables. The hidden layer will help the input layer to move to the output layer. Okay, so the input layer will pass the information to the hidden layer with the weights present, and then the hidden layer will move that data to the output layer. But the hidden layer is essentially a big black box layer, like I told you earlier. You will never be able to understand what is happening with the hidden layer. And the output layer will throw you the final output. So this is another way to a more detailed diagram of the above diagram. So what I'm trying to show here is that there could be any number of nodes that one can be present at every layer, and then there are weights that are applied to the inputs. Excuse me. Okay, so then there are weights that are applied to the inputs that take them to the hidden layer. So if you see in the diagram below, there are 3 inputs, 1, 2, 3, and then there are some weights which are applied to the each of the inputs when it is being taken to the hidden layer. So each input variable with some weight applied will go to each neuron in the hidden layer. So if there are 3 input variables and there are 3 hidden layers, so each of the inputs, like the input I1 will go to each of the neuron in the hidden layer, and a different weight will be applied when it goes through each of the neuron in the hidden layer. And there is another category of weights. So one is the weights that are applied to the input variables. There is another category of weight which we call as the bias values. So bias values are again used to train the neural network. So this can be compared to, if you remember, with the regression also. We used to have a similar thing wherein we'll have some weights that are assigned to each of the variables. So that were the coefficients back in regression, when you used to get an equation something like y equals to a plus b1x1 plus b2x2 plus b3x3 and so on. So when there were coefficients in regression are the weights which are in the neural network, but there was also an intercept which was the unexplained variance or unexplained output that the intercept used to capture. So similar happens here with the hidden bias. So if there is some information that the input variables along with the weights cannot capture, that is captured by the hidden bias. So with each of the layer that you have apart from the input layer, there'll be a bias added. Like if you see in the diagram here, with the second layer, that is the hidden layer present in the between, there's a hidden bias that is added. And with each hidden layer that you have, like here we have just hidden layer, but with each hidden layer that is present, there'll be a hidden bias for each of the layers. And finally, there will also be an output bias which is present for the output layer, nothing but the intercept what we used to have with the regression equation. Okay. That was the basic of what an artificial neural network does. We'll go to backpropagation now to see how the neural network learns. Okay, so the basis of a neural network is a powerful learning mechanism. Although it is a powerful learning mechanism, but you will never be able to understand what that learning mechanism is. But that being said, the neural network has a powerful learning mechanism, and it can learn any function given it has enough hidden units. So each of the hidden units that are present enable it to learn to the input data set. And how it learns is by the mechanism that we call as backpropagation. Okay. So like I told you earlier also, when an input is fed to the neural network, that is when the input variables are fed into the neural network, the input some weights will be applied to the input that is coming. Some bias will be applied to in addition to the input that is coming, and finally that data will go to the hidden layer. The same process will be repeated and the data will move to the output layer. When you get the data at the output layer, the difference between what the actual output or the desired output was and the output that you are getting, some error will be calculated based on the difference. Whatever is the error will be fed back to the first layer and the whole process repeats again. Okay, so these errors are fed back to the neural network, and then these weights, to the question that you were asking, the weights are then changed in order to try to reduce the errors and give the correct output. So in the first iteration, random weights will be assigned, but with each iteration that happens, the weights are changed using the errors that we have got in the previous layer. So this is the diagram that explains backpropagation. So there are some input variables, then there is a hidden layer. So say there are 3 input variables here, then there are 2 hidden neurons with the hidden layer. So each of the input variables is being fed to the hidden layer, and then there's also a bias which is being applied, and then from the hidden layer we're going to the output layer. At the output layer, the error calculation happens, which is nothing but the difference between the actual value and the calculated value. Whatever is the error calculation is back propagated, and then the weights are modified. This happens each time the algorithm runs, and that's how the weights are improved, and that's how the algorithm learns. Okay. So then once you're done with backpropagation, so all you did with backpropagation was to get the error and pass it back to the input layer so that the weights are modified. Now how the weights are modified is, after you've done the backpropagation, you need to update the weights. Now if you remember with the previous slide that we've seen here, there are weights applied to the hidden layer, and then there are weights applied to the output layer as well. So both of these weights are different. Okay, so don't get too confused with what the equation here is, but this is just meant to show that there are 2 different weights that are applied to both of the layers. So Wij that you see here is the weight that is passed to the variables from the input layer, and Wjk is the weights that are applied to the neurons from the hidden layer. Okay, so both of them will learn from the errors that they are doing, and both of the weights will be updated. Don't go very deep into what the mathematical terms here are, but this is just meant to tell you that both of the weights will be modified based on the error that we are seeing from the previous iteration of the algorithm. There's another thing which you would be which you're seeing here, which is the alpha value. So alpha value is nothing but the learning rate. Learning rate means to say at what rate do you want the neural network to learn. So this is nothing but the learning speed. Okay, if you make the learning speed too quickly, or you make the alpha value, you don't really specify these values, this is what happens in the background. But if the learning speed is very quickly, the learning speed is very fast and alpha value is closer to 1, the algorithm would not be able to learn properly. This is nothing but trying to say that you're trying to learn something very quickly, so you just run over it. You don't understand the essence of what was there in the data. And if you make the learning rate very small, you don't allow the algorithm to grow, you don't allow the algorithm to learn only. So an optimal learning rate is chosen, but you don't choose it, the algorithm chooses it itself. But an optimal learning rate is chosen for each iteration that happens with the neural network. So when backpropagation will occur, some errors would have occurred, and then a backpropagation will occur. That error will be passed back to the algorithm. The weights that are being passed, that are being applied to the input data variables will be modified. The weights that are being applied to the hidden layer will also be modified, and finally a new output will be produced. And this process repeats across multiple iterations, and each time the weights will be updated. Okay. Then we come to the error function. Error function is nothing but again the difference between the actual value and the desired value here. So although this is a repetition, but the input variable will be passed through a system. So adaptive system here is nothing but the hidden layer, and then you get a output y. You compare that output to the desired output. Whatever is the error is passed back to the adaptive system, nothing but the hidden layer. Then the weights are modified. So one thing to keep in mind is that the error should satisfy some particular properties. This was present in the videos as well that we saw. The first thing being that the error should be derivable, meaning to say that it should be possible to do a derivative. Derivative is nothing but d by dx, what we used to do back in 11th 12th mathematics. So it should be possible to do a derivative. Why? To answer to one of the questions earlier, the threshold that we calculate, the threshold that we specify is a derivative of the error. Okay, so if it is not derivable, so the threshold thing will not work. The threshold that we are specifying, that we are telling the algorithm, is nothing but derivative of the error that we are getting in each layer. Okay. So this is very obvious although, but as the output moves towards the desired value, the error should obviously move to 0. Error should be negative, again for the reason that we should be able to do a derivative of it. And then we need to choose the error value. Sorry, we're not choosing the error value actually, but then when there is a too low value for the error, or there are too high values for the error, that actually impact how the neural network works. If the error value is too high, the accuracy of the neural network will be bad, and then it will take a lot of iterations to be able to learn. And if the error value is too small, sorry, that I've put it opposite. So if the error value is high, then the neural network will take a long time to learn. I'll just change it after this session. Okay, so we'll finally see an overview of what happens with the learning algorithms. The learning algorithm overall. So the back propagation actually allows the neural network to get trained, similar to how we train all the machine learning or the data mining models. Similar way, the back propagation allows the neural network to learn. This happens in multiple iterations, what I've been calling so far. These iterations in terms of neural network are also called as epochs. So it goes through several epochs before the network has sufficiently learned to handle all the data that is provided. This is again a different diagram shown in a different way to show how backpropagation works. But that will happen. This is that will happen for each of the iteration or each of the epochs. The input data will be fed, the output data will be compared against the desired value, and then it will be whatever the error will be back propagated using the error to update the weights. Now, when will this stop? Meaning to say that each time when a particular error is calculated based on what was the output versus what was the desired output, and then a back propagation occurs. So this process keeps on repeating. So like we used to have a pruning step or a stopping criteria for the decision trees that we saw last week, similarly there should be a stopping criteria here as well. So multiple stopping criteria can be used for neural networks, one of them being a desired mean square error and one of them being elapsed epochs. Desired mean square error tells what is the error that we can allow the data to have, what is the flexibility that we're giving the data to have, and elapsed epochs is nothing but what is the number of iterations that we want. So a neural network cannot run indefinitely through 10,000 or 1 lakh iterations. So this varies with the data that you have, but it cannot run indefinitely. So we need to specify the number of iterations for which a neural network should run. So both of these are used as stopping criteria for the neural network. Okay, so again, I'm using the iris dataset that we had seen with the previous algorithms as well. To give you a quick revision of what the iris dataset was. So this dataset has 150 entries in which there are 4 input variables, which are sepal length, width, and petal length and width. And finally, there are 3 species, 50 of each species. And the aim of this algorithm is to try to predict what is the species of a particular flower given its attributes of sepal and petal length. So with the last session, we tried to predict the species using CART, using random forest. We also saw the same example with clustering as well, wherein we were trying to use the sepal length, width, and petal length and width to try to cluster these flowers together. So we'll use that same data set. I'm repeating the steps what we did earlier of generating a random number, shuffling the data. So this again is a optional step, but I normally do it so that there's no biasness which is present in the data. One important step which you can note down here is the line number 12 that I have with the R code. So if you remember with neural network, this was being done in the example that we did, and this will also be useful in the example that you do with your mini project. So if there is any variable which is categorical variable, something like the species that you have here, where it is setosa, versicolor, and virginica. When you have 3 species, you cannot have the data in this format when you work with neural networks. So you need to have 3 columns which are in forms of 1 and 0. So either you can do that with multiple commands, either you can create 3 new input variables and then pass 1 and 0 here, but a simple command is the class dot ind command, which you can use in one go to create all the 3 variables. Let me show that to you how it happens. So if you see here, with a single command, I'm able to segregate the initial species that I had. If you see, the species I had here was in the form of Setosa virginica and versicolor, and then I've split that data in form of 0 and 1 with one single step. Okay, so what was done earlier was we used to do that for each of the variables one by one, but using this command you can now very simply split the data in the required format. Okay, and as a shortcut, what I've also done is I've done the scaling in the same command here. So what I essentially did was, from the initial IRSR data set that I had, I scaled the first 4 variables. So the first 4 variables of sepal length, width, petal length, and width was scaled, and then this width, the output variable, which was 1, was split in the form of 0 and 1 to be able to fit the neural network. So then I am simply dividing my data set into training and testing data set. So roughly a 70-30, but not exactly. So first 100 I'm passing to my first 100 rows I'm passing to my training data set, and next 50 to my testing data set, and finally I'm creating a neural network. So we'll see here what is the parameters that we pass to the neural network. So the first thing is the formula that we need to give here. So the formula here tells me that these 3, which now become my output variables, see Setosa, versicolor, and virginica, which now become my output variables, are a function of 4 independent or the input variables. So this is the formula that I've specified. Data is the training data set. Hidden specifies the number of hidden layers that you want. So a thumb rule to choose the hidden layers is under root of the number of input variables that you have. So if you have, I had 4 input variables here, so I chose 2. Okay, and since you saw you can have multiple hidden layers here, so say if you have maybe like here I had, 1 second, input variables and hidden layers. So since I had 4 input variables, I did a square root of this to choose that I'll have 2 hidden equals to 2 here. Give me a second. Okay, and sorry, so 2 here means I'm rounding it off to get a 2, so that will mean that I have 1 hidden layer with 2 neurons. Say you have maybe 20 input variables in place of 4, so you do a square root of 20, which will be 4.47. Now you round it off to 5, then you do a square root of 5, and that will be 2.23. So you can round it off to probably 2 or 3. So what I'm trying to tell you is that when there are 4 input variables, I'll have just 1 hidden layer, which will have 2 nodes. When you have, say, 20 input variables, you'll have 2 hidden layers, the first of which will have 5 hidden neurons, the second of which will have 2 neurons. Okay, making sense? Like if I have 100 input variables, I'll have first hidden layer, which will have 10 neurons. Then I'll have second hidden layer, which will have 3 neurons. Then yeah, so that will be here. Say I have 500 input data variables, so I have first hidden layer which will have say 22 hidden, sorry, I'll have first hidden layer which will have 22 neurons. Then I'll have second hidden layer which will have 4.7, or you can round it off to 5 neurons. Then again I'll have third hidden layer which will have 2 neurons. So this is how you decide the number of hidden layers that you have with the data and number of neurons that will be present in each hidden layer. Let me kind of erase this and do this again. Okay, so input variables and then the hidden layers. So when I had 4 input variables, I do a square root of 4, that will be 2. So I have one input layer which has, so this will be the first hidden layer with 2 neurons. Okay, so you kind of keep doing the square root multiple times. So I'm doing a square root here the first time. Second time when I do a square root of 2, I come to approximately 1. So then I stop. Okay, meaning to say when I have 4 input variables, I get a 2. So that will be first hidden layer with 2 neurons. Say if I have 10 input variables, I'll do a square root which is approximately equals to 3. So I'll have a first hidden layer with 3 neurons. And then I'll do a square root of 3, which is 1.7, and you can round it off to 2. So I'll have a second hidden layer with 2 neurons. Okay. Now if you do a square root, you keep on doing the square root iteratively. So now if you do a square root, you will get something like 1.4 or something. So there you stop. So with 10 input variables, you'll have 2 hidden layers. So with the hidden layer parameter that you're specifying here, I did a 2 here because I had just one hidden layer. So you need to give hidden equals to 2 here. With the 10 input variables, you need to give hidden equals to C of 3, 2. 3 means first with 3 neurons, second with 2 neurons. Okay, like a bigger example, if we take, I have 500 input variables, so I do a square root of 500, that will be say 22.36, and I'm rounding it off to 22. So I'll have first hidden layer with 22 neurons. Then I'm doing a square root of 22, that gives me 4.69, and if I round it off to 5, so I'll have a second hidden layer with 5 neurons. Then I do a square root of 5, square root of 5, which gives me 2.23, so I round it off to 2, for example. So then I'll get a third hidden layer with 2 neurons. And then when I'm doing this with R, I'll give hidden equals to 22, 5, 2. So this means 3 layers, first having 22 neurons, second having 5 neurons, third having 2 neurons. Okay. So next is the threshold. So threshold is nothing but a derivative of the error that will be calculated at each step. So we can also see that from the help in R. See the threshold. So threshold is numerical value specifying the threshold for the partial derivative of the error function as a stopping criteria. So at each step, some error will be calculated as a difference of the actual value and the desired value, and then you calculate a derivative of it. So say the error in the first step is 2, for example. So you calculate a derivative of it, then backpropagation will occur, then a reiteration will occur, and this process keeps repeating. So this threshold equals to 0.01 says that keep repeating until you receive a derivative of the error function, which is 0.01. Okay. So in the first iteration, maybe derivative of the error function will be, say for example, 1. Then you backpropagate, reiteration occurs, then the derivative of the error function maybe comes down to 0.9. Then you repeat it, backpropagation occurs, then maybe the derivative of the error function comes down to be 0.6, then 0.2, 0.1, and till it comes down to 0.1, you need to keep repeating the algorithm. Okay. The next step is, so this is one stopping criteria. Threshold is one stopping criteria. Step max tells you what is the number of iterations you want. It is possible that even with 10,000 iterations or 10,000 cycles, the threshold doesn't reach 0.01. Doesn't mean that you'll keep running this algorithm infinite times. Step max is another stopping criteria, which tells us what is the number of iterations that we can allow a neural network to have. So step max equals to 2000 tells us that we need to, we can run this algorithm a maximum of 2000 times. Okay, so linear output equals to false is nothing but telling whether or not you want the activation function to work. So to revisit, activation function was nothing but allowing a neural network to fire a trigger. Firing a trigger means allowing a neural network to backfire. So, sorry, backpropagate. So when you specify linear output equals to false, that means that you're allowing the activation function. Okay. With the lectures, there were different activation functions that were also given, but there is not much difference, practically speaking, with the different activation functions. And even if you don't specify it explicitly with your commands, you're not missing out anything. Just specify that linear output is equals to false. This is enough to tell R that you want the activation function to work. Okay. Then life sign equals to full and life sign dot step equals to 10 are again optional steps. These are only to tell R that, say I am telling here that I want 2000 iterations. So these two steps are only to tell R that I want to see the output after every 10th iteration. If you skip this step, even then the algorithm will run, but it will not show you what is happening with each step. So when I'm telling R that I want the life science step to be 10, so after each 10 iterations, like after 10 iterations, after 20, after 30, after 40, so on till 2000, R will show me what is happening with the neural network. If you skip this, it will directly give you an output. Okay, then error.fct is nothing but telling you how do you calculate the error function. Okay, so error function is nothing but difference of the actual value and the desired value. But how do you calculate it? SSE is sum of squares error, and this is the best you can do with neural networks, because with neural networks you want your error to be positive so that you're able to do a derivative of it. So the best thing to use is an SSE, which is sum of squares error. So supplying all these parameters, when I run this command, sorry. Okay. So I ran this command. See, there are two hidden neurons. That was what I had specified with each iteration. So I told that I can do a maximum of 2000 steps, but my algorithm stopped with 125 steps. So when there were 10 steps, when 10 iterations had occurred, my error was 2.869. After 20, it reduced to 2.795. After 30, it reduced to 1.487. And finally, after 125 iterations, my error reduced to 0.03541. So the stopping criteria which worked here was this threshold. So a derivative of 0.0351 would have been lesser than 0.01 and hence it stopped here. Okay. So once the error of 0.03541 was achieved, this was achieved with 125 steps. So I did not have to do 2000 steps. I got the output with each 10 iterations. You see, you could have done a life sign step of 1 to see what happened with each iteration, but then it becomes too detailed. So with each 10 iterations, you see the error was reducing, and finally it came down to 0.0351, and this occurred in 17 seconds only. Okay. Now if I kind of try to plot the neural network, this is what I get. So see, there are 4 input variables: sepal length, width, petal length, and width. I have just one hidden layer that has 2 neurons. These are the weights, the ones that you see, 1.83 on the top. Second. Yeah, so this 1.3 that you see, 1.83 that you see here is the weight. These are all the weights that you're seeing. Then the 6.6 that you see here, the -12 that you see here, sorry, these are the biases. So 1.83, 0.76, the one that you see on the black lines are the weights that are being applied to the input variables. The ones that you see in blue, 6.6 and 1.2, these are the biases which are being applied. So there's just one hidden layer with 2 neurons. The biases are being applied at both the layers, the weights are being applied to both the layers, and finally an output is being thrown out. Okay. One thing to note here is that if I run the same command again, the weights will be different. Okay, so if you run the same command at the same time with me, even then this will be different. So far what is happening is iris_n is a neural network model which is being created. It's just showing you that these were the 4 input variables, these were the 3 output variables, and something is happening and this neural network is getting trained. Okay. One additional step which can be done here is not with the small data set that I'm using, but if you have larger data sets, one another parameter that you can pass with the neural network command is this parameter called start weights. Okay, so what this is doing is that even though with back propagation the errors are being passed and then the weights are being modified, but additionally you can also pass the weights of the first step to the second step, meaning to say whatever were the weights that were being applied in my first step, I can also pass them as a parameter when I'm back propagating to the second step, so that the same weights are not being used. So this becomes an additional learning for the neural network. So this is not applicable in the small data set that I'm using, it won't do any benefit. But for the larger data sets that are present, these steps become helpful, and I'll show you how you do that. So you create another variable, old weight, or you can name it anything. And in the iris_n was the name of the model that I've created that has some weights. So I'm passing those weights to a new variable, and then I can create another neural network which has the same parameters. Additionally, I'm adding a parameter called as start weights, in which I am passing the old weights, that is the weights that I received in the first iteration. So this is an additional step you can do to improve the performance of your neural network. Okay, so far with iris_n, I've just created a model. Now we'll see how does our model work. Okay, so what I'll do here is with the data set here, I had used the training data set to create a model. Next, I'll be using the test data set to see how my model performs. So because I had scaled my training data set, so I'll also be scaling my testing data set and try to predict the outputs of the testing data set. So I'm using a compute function to predict the values of the output, the testing data set. Iris_n is the model that I had created, neural network model that I had created, and the data that I'm passing is the test data set. First 4 columns, which are nothing but the sepal length, width, better length, and width. Okay, so finally, when I try to predict the values of my test data set, this is what happens. Now, since this is a scaled data set, so the numbers are achieved in this way, but you can again use these numbers as well to also do a prediction. Let's see how do we do that. So you see we had 3 species which were possible, and in the results that I get these are 50 entries which was in the test data set, and I get some scores for each of the species. Like for this particular flower, I get 3 values for each of the species. So the probability that it is a setosa is 0.001. The probability that it is versicolor is 0.01, whereas the probability that it is virginica is 0.99, which is 99%. So this flower, which is in the row number 131, will be a virginica. Similarly, the flower which is in this row 10th will be a setosa. The flower which is in row 95 will be a versicolor. The flower which is in 142 will be again a virginica. This one will be a versicolor. So what I'm essentially doing here is I'm trying to use the neural network model to predict what will be the class of my flowers in my testing data set. Okay, so pass the testing data set. I pass the neural network model, which contains the learnings that it has from the training data set, and I'm using this to predict. So this is the main step. Do not get confused with the other steps, because I'm just doing kind of formatting to give you a nice looking output there. But with this step, I'm trying to predict the values in the testing data set using the learnings I have from the neural network model. Okay, so with the results that I got here, I'll kind of try to compare it. So these are the predictions that my neural network model is making. These are the predictions that I'm trying to make for my testing data set using the neural network. But I should also be able to compare it to the actual values to see how good my neural network is doing. Okay, what I did with this step was nothing but I tried to, like I was telling you theoretically here, on how this would be a virginica and this would be a setosa and this again will be a versicolor. So I kind of tried to put that in words so that we don't have to read through the numbers. So these three commands that I'm doing here are doing nothing but producing this result from this result. So the first one should be a virginica, the second should be a setosa, the third should be a versicolor. This is what I'm doing here, telling R that whichever is maximum out of the three columns, I want that column name to come in my result. So this is the result that I get as a result of prediction after my neural network for the 50 entries that I had in my test data set. These are the predicted species of the flowers using my neural network model. Now I'll be using these 50 predicted values against the initial against the actual values to see how good my neural network is doing. Okay, so these are the original values which were present, and these are the values that I've got, and we'll finally compare them in the table. So you see we have out of 50, so this matrix, if you don't know it already, we call it as a confusion matrix to see how good our models do. So we see there is an error of 3 here out of 50. There is an error of 3, so 47 values are being calculated fine, and hence the accuracy of this model is 94%. To tell you quickly again what I did here, I used my neural network model to predict what species each of my flower belongs to in the testing data set. Then I compared it with the actual species which were present, and finally I get this table which tells me that I have an accuracy of 94%. Okay, so weights will change according to the error, whatever the error is. The end aim is to get a threshold of 0.01 passing whatever weights possible. So it is entirely possible that when you run this algorithm the second time, if you remember here, we had done this with 125 steps. Okay, when you run this the second time, it may take lesser steps, it may take more steps, but towards the end your result will be the same. Okay, because the algorithm will stop when it achieves a threshold of 0.01. Just to tell you, I'm running this algorithm 4th time since yesterday. Once it has run with 300 steps, once it ran with some 95, 96 steps, and once it is running with 125 steps now. But your end accuracy will be the same. The same confusion matrix you'll get no matter how many times you run the same algorithm, because it will use the threshold to stop, and the weights can be anything. Okay, so for today's session, I'll just be doing an exploratory data analysis that will help you just see which variables should be used and which should not be used. Towards the next session, we'll try to actually solve it to see which what is the output that each of the algorithm throws. Okay, I'm importing the data set. Okay, so when I'm viewing this data set, it contains approximately 3000 or like 2940 rows, and it has 35 columns. Structure is just an additional step to see what the structure is. So we have a total of 2940 rows, and then we'll now go to each of the variables individually. So when I start off with the attrition variable, one thing to note here is that these variables have been arranged in an alphabetical order. So you need to, if for better understanding, you might want to rearrange these columns so that similar columns are together. I haven't done that, but maybe you can do that, arranging the similar columns next to each other so that it becomes easier for understanding. So we see here when we start off with attrition, so there are a total of 2940 employees, out of which 474 had an attrition. Okay, so that becomes 474 upon 295 2940. So approximately 16% of people had an attrition, and we'll see what impacts the attrition of these 16% of the employees. Okay, so we'll start off with each of the variables one by one and see whether or not that variable should be included here. So I'm starting off with the age, which is the first variable here. So you see the minimum age is 18, the maximum is 60, and the median excuse me, the median is 36, which is somewhere in the mid. So the data looks like not being very skewed. We do a box plot of it and we see that it looks like a normal curve, the age. So there are people from the ages 18 to 60. And the data is normally distributed. Now I'm trying to see so this is another way. I did a box plot, and this is another way to do a clearer histogram. We could have done it using the hist function as well, but you can also use dplyr to do a histogram, which gives you a more precise histogram to see the distribution of the age. And finally, I'm again using dplyr to see the impact of age. So what I did here was, for the continuous variables that were there with the data set, I'll try to see what is the impact that those variables have. So when I do a ggplot of the age, I get an output something like this. So what this tells me is the pink color shows the employees that have an attrition and that do not have an attrition, and the blue color shows the employees that have an attrition. So what this tells me is that the people who have an attrition, or who had an attrition, are belong to the age somewhere from probably 28 to 39, and the ones that who do not have an attrition have an age somewhere from 31 to say 43. What this tells us is that when you're seeing just the age variable alone, there is a difference in the ages when the people have an attrition or not. So people in the younger age groups are more likely to have an attrition compared to people in the larger age groups. So this helps us understand that when we see the impact of age alone with attrition, so age is an important variable when we are trying to study attrition, because there is a significant difference with this graph. So the age should be included as a variable, as an input variable when we are trying to do the modeling. Okay. Next, we'll go to the second variable, which is business traveler. So it is a categorical variable that tells us whether or not a person travels for business and how often he travels. So out of the 2940 employees that we have, so we see that most of the employees travel rarely, and then we'll try to understand whether or not traveling has an impact on attrition. So since this is a categorical variable, I just created a simple table to see if there is an impact of business travel and attrition. So we see the ratio that you see between a no and yes here. So for non-travel, the ratio of 276 to 24, and 416 to 138, and 1774 is to 312. This is almost similar. There is no much difference. Let me do an actual numbers. 276 by 24. 416 divided by 138. 1774 divided by 312. So there's not much difference in the people who travel to see whether or not they have an attrition. So you can choose to ignore this variable because it doesn't look like it is having an impact on whether somebody or not has an attrition from the organization. Okay. Age we saw has an impact, but the business travel does not look to have a significant impact with the business travel does not look to have a significant impact with attrition, so you can choose to ignore it. Okay. Similarly, we go to next the daily rate. So daily rate is again a continuous variable which shows the rate at which an employee is being paid on a daily basis. So when we see a summary of it, it is again a continuous variable, the minimum being 102 to a maximum being of 1500. When I do a box plot, it looks like a normally distributed data, and you can also see that from an histogram as well. But a good thing to see here is if I do the impact of daily rate on attrition, probably the daily rate does not have a very significant impact. Let me go back to the histogram again to show you. So see, almost all of the daily rate is uniformly distributing, meaning to say that across all the 2900 employees that we have, the daily rate was evenly distributed. And when I did a comparison of people who had right or not from the organization based on the daily rate, there is no significant difference. There is a very small difference here. If I zoom it out, so this is 400, so 600, so this is somewhere around 450 or so. So there's not a very significant difference compared to the range of daily rate that I have. There is not significant difference in the daily rates of people who have an attrition or not. So even daily rate you can choose to ignore when you're doing the modeling. Okay, with age we had a significant difference. With daily rate we do not have a significant difference. And also we saw from the histogram that the daily rate is not very varied. It is almost constant. The frequency of the daily rate within the employees is almost constant, so it doesn't look like having a very significant impact. So you can choose to ignore the daily rate variable as well. Okay, next we go to the department, which is a categorical variable. So we'll just see a summary of it. Okay, so see, this is significant here with the human resources, 1656 divided by 266, and so this is evident from the data as well, but I'm trying to show it more clearly. Okay, so with the department as well, the ratio between no and yes is almost similar. Okay, the people who had right versus the people who do not had right is again similar. So department again you can choose to ignore because there is no significant difference with respect to, there is nothing like people of a particular department have more attrition compared to people of other departments. So you can choose to ignore this variable as well. Okay, so then, or maybe, okay, 284 is also okay. So then you see that there is a different, significant difference with the other departments. So if you see that for a particular department, the ratio between no and yes is different for a particular department compared to other departments. So then you say that people of that particular department have a more attrition rate compared to people of the other departments. So that will mean that that particular department has a significant importance when you're when you're creating a model. That department variable has a significant importance and hence it should be included. But with the current data set that we have, there is no significant difference with each of the departments, so you're okay to ignore it. Okay, and this is what happens when in the industries when we are actually working. So this is again a data set with 35 variables, but this is again not huge. We had actually worked with one of the data set that had some around 170 variables or something like that. So we need to most of the time gets spent in doing the exploratory data analysis only, because the models that you're creating, like the neural network I created here, is a 2-liner command that you can execute within seconds. If the data is huge, that command will take a minute or maybe 1.5 minutes to run, but then it is again a 2-liner command that can be executed quickly. Most of the time that goes in the organizations is doing the exploratory data analysis, and that needs to be done for each of the variables here. So here with this data set, I haven't done. So I had seen an overview of what the summary was. So this doesn't look like a data which contains outliers. So in actual data, in the actual data that you'll see, there'll be outliers as well. So how will you understand whether or not the data has outliers is by studying the individual variables. Okay, you study the individual variables. Whichever variable you see looks like having an outlier, that needs to be treated. If there's a missing value within a data set, that needs to be treated. And finally, using the summaries of each of the variables, you need to decide whether or not that variable needs to be included in the data set. So I've done that for each of the variables. So since this is clear now, I'll quickly run through all the variables. So when you do this exercise for the mini project that you're doing, repeat these steps in a similar manner for each of the variables. Then you also have this distance from home. So that tells the distance of the employee's home from the office, which is a number from 1 to 29. And if you zoom this out, this is a very intuitive as well, that people who have, so distance from home to your office is a significant factor, and that is also evident from the data. So you see people who have more distances from home, like the yes is in the blue color. So people who have more distance from home are more likely to have an attrition compared to people who have lesser distances from their homes. So distance from home is a variable which should be used as a factor for impacting attrition. Next is the education level and the education field, which are categorical variables. So we'll just see a table of them here. So with this table, I am not doing the actual ratios here, but do the ratios of these variables to see if a particular education level, you notice has more attrition compared to other education levels, then you need to include education in the as an independent variable. But if all the education levels behave in the same way, then you can choose to ignore it. Similar is the case with education field as well. If there is a significant difference between the attrition of yes and no for any particular education field, then it should be used, otherwise it should be ignored. Now one thing to see here when you do different models, like for example if you're doing a random forest or a neural network, so even if you do not do all these steps, the model will run. So especially when you're doing a random forest and you do not do these steps, the model will run. And the random forest, and for that matter cart also, both of these algorithms choose the best variables by themselves. Okay, because they use the, like cart uses the Gini gain concept, so it sees all the variables itself as well, and chooses which variable is good, which variable is not good for splitting. So with those algorithms, even if you don't do these steps is okay, but doing them is a better thing. But if you don't do them is okay. But with neural network, if you simply pass all of the variables at once, if you pass all of the variables, the neural network model, the model will run, but the accuracy will not be good. So this step becomes essential when you're doing a neural network to achieve accuracy. Okay, because with neural network, there is no particular algorithm to decide which variable is important, which variable not important. Whatever the variables that you're passing through the neural network, it will learn from all of the variables. The backpropagation, the error rates, the gradient, everything will be calculated on each of the input variables, and it has no method to decide which variable is good and which variable is not good. So then the model accuracy is not very nicely. So very nice. So especially when you're doing a neural network, do this as a mandatory step. Okay, and unless you do this, you won't be able to also see. So there could be some variables which are correlated, there could be some variables which are intuitive, there could be some variables which can be calculated from each other. So you won't be able to understand that until you do an exploratory analysis. So see, like for example, I show you one of the variables here. For example, this employee count. So employee count is doing nothing, but it is telling whether or not this employee is distinct here, just to check that there are no duplicate entries. So that this variable doesn't make sense when you're passing it to a model, because just by doing a quick check once on this particular variable, you can decide whether or not there are unique employees or not. Random forest doesn't know that. So random forest will try to consider in one or more of the trees that it is creating. Random forest will try to consider it as a variable, wherein you yourself know that it is not important. So why just pass it at all? Okay, similar is for one more variable, which is I think over 18 here. So you have an age variable, which is enough to calculate the impact of age, and the over 18 anyway contains all y values. So that it is not significant. The random forest doesn't know that it is not significant or it doesn't make sense. So why just pass it at all? Okay, because in case it sees that it is significant, but that it is not significant, so it is advisable that you do not pass such variables at all. There's another thing I'm showing you for an example which you should avoid when you're doing the modeling in addition to the data set. Say you have a salary of, like you had monthly rate here, say you have salary of January, salary of February, salary of March, and so on till salary of December for the employees, and then you also have a total salary in your data set. Assume that the salaries for each of these months are different, they are not the same. Say this is 1000, this is 1200, this is 1150, this is 1300, and so on. So these are not same, and then you have a total salary which is sum of all the salaries, and you have all the variables here. Now these variables may not necessarily be correlated. It is possible that for one employee, probably the salary of February was more. For the second employee, maybe the salary of February was lesser than January. The salary of March shooted for any reason, and then the total salary will be accordingly. So if you see salary of January, salary of February, salary of March in this data set, it will not be correlated. But the important thing to note here is that total salary contains the essence of all these variables. So when you have a data set something like this, ignore all of these variables, include just the total salary. Okay, so this is an additional step apart from correlation. The salary of Jan and Feb may or may not be correlated here. The salary of Jan and total salary may or may not be correlated here, but then the total salary captures the essence of all of these variables. So if you have a data set something like this, ignore all of these variables, include just the total salary. So I did this for all the variables here. Like we have the employee count, like I showed. So employee count is just to see whether or not there are duplicates in the data, and there are 2940 employees, and the count is always 1 here. So unless you do an analysis of this step alone, you won't be able to determine this. So this variable has no importance at all, and you should ignore this. Okay, so I kind of did that for all the variables. For environment satisfaction, this again is a categorical variable, and you can decide whether or not to include it. Same was for gender, it was a categorical variable. Same was for the hourly rate here. So you see the hourly rate, it is very much similar. Whether or not there is an attrition, the hourly rate is very much similar. There's no difference. So don't include this variable when you're doing the modeling. One more thing I wanted to show you was what we had seen earlier as well. So I'm doing this for all the variables, and you can decide whether or not to include them. Okay, for the monthly income. So you see the summary of monthly income, it ranges from 1009 to say 20,000 approximately. When I do a histogram of it, okay, so we had seen this when I showed you the air pollution regression example. We had seen this, but see, the histogram of monthly income is highly skewed. Okay, so this again should be considered before you do the modeling, that there should not be any skewness in the data, because if it's not normally distributed, the data will be biased to learn more from the monthly income. Like here, probably the monthly, more people have monthly income in the ranges of probably 2500 to 7500 contains most of the people. So the model will learn more from the employees that have salary ranges between 2500 to 7500, and lesser from the employees that have salary ranges in the other that have salaries in the other ranges. So the data should also not be skewed when you're doing the modeling. So when I do a log of it, the skewness gets removed, and hence when you're passing this variable, you should not pass the monthly income, you should pass log of monthly income as the independent variable before doing the modeling. Okay. So couple of things to check is, one is the missing values, one is the outliers, then see whether or not they are correlated, the variables are correlated. Then also see what I told you in the example, if one variable can be computed from the other variables, then use just one of them. Then also see whether or not the data has outliers or not. If it has whether or not the data is normally distributed or not. If it is not normally distributed, do a transformation and then pass the transformation as a variable rather than the individual variable. Okay, so monthly income you see has a significant impact on the attrition. The people who have a smaller monthly income and the people who have a higher monthly income. Okay, I've done that for all the variables. This is again over 18 variable, which contains all Y's, that all of the people are above 18. So that is a totally non-significant variable. We see one overtime variable again. See, this tells you that overtime out of 578 and 254, and then this is approximately 1900 and 220. So people who do overtime have a more likelihood of having an attrition rather than people who do not do overtime. So overtime is a significant variable. The same thing what we saw for monthly income also applies to percent salary hike. So see, this again is a heavily skewed data set, so you need to do a transformation of it before you actually pass it. So I use this Box-Cox test which we had seen earlier when we did regression. So I used the the lambda value here, and when I plotted transformed value of the percent salary hike, the skewness looks like having been removed. So then instead of passing the percent salary hike, I should be passing a 1 upon percent salary hike as an independent variable. Okay, so you need to do that for all. One more variable here was for standard hours, which is 80 for everyone. So you can ignore it. Do that for all the variables. Okay. One easy way to check for the missing values is a command that I've put here. Either you can do it for all the variables one by one, but this is one simple command to check the missing values all at once. So when I run this command, I'm just checking whether or not there are any NAs in any of the values, and I'm creating a matrix based on that. So it shows you for each of the variables whether or not there are any missing values. Okay, so it shows 0, 0, 0s in all of the values, means that there are no missing values in any of the variables.
This brings us to the end of this course. Thank you very much and have a great learning ahead.
I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.